All right, so welcome back, everybody. Hope you guys had a good break. So time to get back to work, and we'll have a very exciting course. Our course, as you know, is reinforcement learning. So CPEG 591, reinforcement learning. Okay, so reinforcement learning is another field of AI. So many of you have taken different courses, hopefully before, for example, deep learning or advanced deep learning. Okay, I think many of you were in the previous semester's course, which was the natural language processing. Okay, some of you might have taken computer vision and perhaps some other courses such as data mining. Okay, some of you I know are coming directly to this course without having taken these courses, which is fine. Like any of the previous courses, I'll cover all the necessary background. So our goal, as always, is start from the very basics and go to the state of the art or as much as we can. So from beginning to advance, we'll be covering the material, right? For those of you who have taken courses from me, I'll provide as much helpful information as possible. We'll take a look at different algorithms. I'll provide the code, the implementations. This time I'll try to see, because many of you are also pursuing PhD or are very interested in research, because as you know, the job market is getting more and more difficult. Hopefully it will improve. But many of you MS students, if you're looking to, stand out, if you can also be involved in some research and put it on your resume, that will also help you a lot. Okay, so hopefully after we are gone through half the semester, you'll have enough idea. We'll take a look at some research papers. Even today, I will show you one research paper, and if some of you wanted to start right away, you could do that. Anyway, get involved, learn nicely, and I'm here to help you understand and get the very best you can out of this field, right? Okay, so now next question is, what is reinforcement learning? Okay, NLP was pretty straightforward, right? Because we were trying to create an architecture where we can have it understand text. It can do sentiment analysis as an example, or if we ask it a question, it can answer it. So we looked at, for example, in the NLP field, if some of you who took the course last semester, our fundamental architecture was based on a transformer. Okay. One of the reasons the transformer worked really well in the NLP was, if you remember, what we did is, so first of all, in all of AI, it doesn't matter what type of data we are trying to have it understand. The data, the input data has to be converted to numbers, right? So in case of NLP, let me quickly refresh your memory. What did we do? If you're given some text over here, it has to understand the text before it can answer any question about it or understand the sentiment of it, right? So what did we do? We somehow took each word and converted it to a set of numbers, which we call a vector. And we refer to this as the embedding dimension. So for example, if we decided every word will be converted to, let's say, a set of 512 numbers, then in the very beginning, before we feed it to the transformer, this is what we will do: convert each word to set of 512 numbers if we decide the embedding dimensionality to be 512. Okay. For example, the very first ChatGPT 3.5 used a dimensionality of 4096. Okay. So anyway, if we are creating a smaller model, we can pick a smaller embedding size. If we're creating a larger model, more elaborate, we can pick it to be larger, right? Okay, so we start out by representing each word as a set of 512 by 1 numbers, right? So in the beginning, they are all separate, or, they're not relating their information with the surrounding words. But as we know, in understanding text, we have to know in what context a particular word is appearing. For example, if we are saying bank, is it a river bank? Is it a bank where we deposit money? So we have to understand what is before and after this word. So the whole idea in the transformer was start out where everybody is independent, meaning the set of words do not know or their representation, this 512 numbers, is independent of, in the beginning, what is next to it, right? So gradually we pass it through layer 1 of the transformer, then layer N of the transformer. And in a transformer, the input size and the output size is identical, meaning let's say we had 100 words over here that we fed, then the total, because each word is being represented by 512 by 1, then the total number of, like if we assemble it as a matrix, this will become 100 by, 100 by 512, right? So as we go through from layer 1 of the transformer, the intermediate output will also be 100 by 512. Meaning over here, we'll still have, you can think of it, the same 100 vectors. However, now as we go through each layer, it is trying to take a look at, what is next to me, what is 2 words away from me, so that it keeps adjusting its representation. So that now it is trying to put the context together. And so as we keep going, finally, at the very output, okay, if our goal is to do the classification, we'll pick one of these representations, usually the last word, and connect it to a classifier. Okay, and then it will, for example, if we are doing sentiment classification into, is it positive, negative, neutral, strongly positive, strongly negative, then the classifier will have 5 outputs as an example. If we are trying to create a ChatGPT as an example, where we start out with 100 words as a prompt, as an example, then what it will do is it will create 1 word only in the output. Then we drop out the first word, and whatever word we had generated becomes the input. And based on this, these 100 now will predict the next word. Now, again, we will drop out the first 2 words so that total becomes 100. And based on these, we'll predict the next word. So this mechanism is called autoregressive generation, where one at a time, we keep generating. And if we wanted to write an essay with 500 words, it will repeat this process 500 times until 500 words are generated. And that will be the output from something like ChatGPT as an example, right? So coming to reinforcement learning, why is it a very, very important field? So, excuse me for some reason. Okay, so why is reinforcement learning needed? Okay, if let's say we were creating something like ChatGPT, right? as I mentioned, the way we train ChatGPT is the whole training is done, meaning its learning is done to predict next word. Okay. Like I said, if we feed it hello there, it will learn to predict how. Then if we feed in hello there, how, it will learn to predict R. If we feed in hello there, how are as the input, it will learn to predict U. So this is how one at a time ChatGPT uh, generates the output, right? If we train ChatGPT, which is again a transformer type of architecture created in an autoregressive type of training, then it will be good at predicting the next word, but it will not be able to write nice, coherent essays, for example. Okay, so if we, for example, ask ChatGPT, okay, write an essay on the future of quantum computing. It may start out pretty well, giving us 4, 5, or maybe 10 words, which are pretty good. But then the next sentence, remember in good writing, this has to have a flow. The first sentence should be related to the second sentence. The first two sentences should be related to the third sentence. If first sentence is talking about computing, second sentence is talking about weather, that's not good writing. Okay. So what I'm trying to say is autoregressive type of training does not guarantee that there will be a good flow as we generate a lot of data, a lot of outputs, okay? So we need some other mechanism so that at a very large scale, this whole flow that we have in the outputs that we are generating is cohesive, meaningful, related to each other, it outputs more like a very, very good writer who's, writing coherent, meaningful, to the point type of output, right? So this is where reinforcement learning comes into play because the autoregressive generation does not care about the flow. It only cares about what will be the appropriate next word, right? Now, as soon as we are done with the sentence, this is where it runs into a problem. It doesn't know, okay, period means we're done. So now what should we generate, right? If I have to give you a very high level idea of reinforcement learning, like what is the purpose of it? Why do we need it, right? And the answer is reinforcement learning takes a look at the um, overall flow or overall the entire generation of the output, whatever we are generating, and make sure that there is some sort of cohesiveness to it. So that is one of the jobs of the reinforcement learning, right? Okay, another purpose of the reinforcement learning is, so before I go to the another purpose of it, so ChatGPT itself, okay, is trained in 2 phases. So, okay, the first phase is autoregressive, meaning outputting one at a time. Whatever it outputs, that becomes the input. Based on that, it generates the next output. So autoregressive training is how do we start out with? Once it has learned to most of the time successfully predict the next word, then we go to the what we call it RLHF is the abbreviation, which is basically reinforcement learning based on human feedback. Okay, so remember when you ask ChatGPT, okay, give me some answer. Then if you don't like the answer, you may ask it again. And sometimes it will ask you which response was better. Okay, was the first response better or the second response better? So if we gave it a prompt as an example, and it generated response one, and then response two. Okay, and let's say, so this is where the human feedback comes into play. So a human will say, because we, see, uh, was the first answer more meaningful or the second was a little bit better worded? So whichever we prefer, okay, so we will say, for example, two is better than one. Okay, so now let's pretend for many, many different prompts, okay? So this is prompt one, some other question. So these may not be related. Uh, for some other prompt, again, we have response one, we have response two, we have some kind of a preference. Let's say one is better than two. Okay, so if we can create a data set out of this, let's say we have 100 million of these feedbacks that we have collected. And if we can now put it into a data set, and now we can go and use this reinforcement learning over here to make it uh, learn to generate more where humans like the writing or they prefer the writing. So this is where what we fine tune our generative model on human feedback. And the technique that we use is for it to start generating a more cohesive output is reinforcement learning. So the very first ChatGPT, it used an algorithm called PPO, Proximal Policy Optimization, that we will cover in depth as we go along in this course. Okay, then a new recent algorithm a couple of years ago was released. It's called Direct Preference Optimization. Okay, and it's abbreviated as DPO. DPO showed a little better results as from learning point of view as compared to PPO. So the newer generative models, all these large language models, as of now are using the DPO rather than the PPO. Okay. I have a PhD student where we are looking at some optimization problems, in particular combinatorial optimization. And we wanted to use a large language, a model-based approach to solve these optimization problems. So we set it up. And again, we wanted to follow the same, for example, autoregressive generation in the first phase, then some reinforcement learning in the second phase. And towards the end of the course, I'll show you exactly, one of your assignments, you'll also implement it. So in fact, let me give you a tiny bit idea of it so that we develop a good motivation for reinforcement learning so that as we go along, we know why are we doing this? What's the idea? And perhaps some of you will come up with another better algorithm that, like I said, this is in the early stages. DPO was only released a couple of years ago. I think there are a lot of possibilities for making it even better. So anyway, let me show you as we create AI models or deep learning models, right? In NLP, you guys saw, again, the transformer architecture. You guys saw the first phase. You did not see the second part of it, which is RLHF, which we will go over in part of this course, okay? Okay, so just to give you an idea of the importance of reinforcement learning. Okay, one of the, see, combinatorial optimization is a very challenging field in computer science. And it's referred to as NP-hard problem. And there's a theorem in computer science that if you can solve one NP-hard problem, you can solve any problem. I mean, there's an equivalence to these type of problems. Okay, so ever since we started computing, even before computers, hundreds of years ago, mathematicians have been very interested in, can we come up with a solution to global optimization, right? So a very famous problem, a very famous example of combinatorial optimization is the traveling salesman problem. Okay, it's very easy problem to very easy to understand, not to solve. Okay, and the idea is like this. Let's say you're given 5 cities, and a salesman has to go and travel to all the 5 cities such that, so let's say 1, 2, 3, 4, 5, and you have to come back to one. Okay, and this is called the tour. Okay, and the cost of the tour has to be as less as possible. So cost could be the distance traveled, or it could be, if you're flying, the airline tickets or whatever. So anyway, let's take a look at the distance. Suppose the distance from 1 to 2 is 20 miles. 2 to 3 is 12 miles. 3 to 4 is 7 miles. 4 to 5 is 13 miles, and 8 miles. Okay. So what is the cost of this tour as an example? So the cost will be 32 plus 7, 39, 52, and 60, right? If I calculated correctly. So 60 miles is the total, right? So on the other hand, what if we start from 1, and instead of going to 2, we go to 4, then 3, then 2, then 5, and then 1. Okay, so now 1 to 4 could be, the distance could be 11 miles. This could be, whatever, 9 miles, and so on. And the cost may turn out to be 56 miles if we added this up, right? So the goal of the TSP is to find which order should we cover all the nodes such that the total distance traveled is as less as possible, right? Okay, of course, you can say, okay, let's list all the combinations and calculate the cost and whatever is best. So it turns out this will be 5 factorial if you have 5 nodes over here. Okay, so 5 factorial is what? 5 times 4 times 3 times 2 times 1, right? 20, 60, 120. Okay, so we can write a program to examine all 120 combinations, and whichever has the lowest cost, that should be the best tour, right? Okay, so this can be easily determined, but what if we have 20 nodes, then combinations are 20 factorial. Now try, it becomes impossible on any of the computers. And 20 nodes is a small problem, but if we have 2,000 nodes, 2,000 factorial, and this is where the quantum computing is coming into play. Some of you I know are in the quantum computing course where we look at these type of problems. So quantum computing has this very neat concept of superposition where it doesn't matter if it is hundreds of trillions of combinations, it can examine all the solutions simultaneously, and so that we can see, oh, which one might be the best combination, right? Okay, so anyway, coming back to RL, so the question is, can we set up this combinatorial optimization problem as a large language model and maybe utilize this reinforcement learning that I mentioned, which is the second phase that we use in training a large language model? Can it be applied to, right? So, so let's take a look at this in terms of the traveling salesman problem. So let's pick 5-node problem. Suppose these are the XY coordinates of 1, 2, 3, 4, 5, right? And we are given distances for, like I said, 1 to 2, what did I say? Maybe 12 miles, 2 to 3. We know the distance. We know 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5. So it will be a fully connected graph, as you can see. So our distances are given to us. Okay. And based on how this graph looks like, what do we have to generate from our model? We have to generate the tour, meaning, and in our tour, in a traveling salesman problem, the start node is always the same as the end node, meaning you have to come back to the start node. So let's pretend we fix the start node to be 1. Okay. So if we are using a large language model, remember how do we train a large language model? It predicts next word, right? In terms of NLP. Over here, what will we make it learn? The next node. So we will say, okay, maybe, or instead of 2, instead of going in proper order, let's say it learns to predict 4. So then what will happen? The graph, see, so in the beginning, when it predicted the 4, the whole graph, because it needs to know what's the graph looking like in order to predict the next node. Because remember, it has to optimize the tour. And the tour depends on how are the distances. So graph has to be given as an input in the beginning because we always start as 1. So 1 has to be given to it as the input. And the first prediction will be 4. Everybody agrees? Okay. Now what will happen in the autoregressive type of generation? So in the second step, like I said, what will we do? The graph will still be given as an input because it needs to know that. And what else will be the input? Up to 4. Okay. And now what will it, based on this information, what will it learn? To predict the next node. So the next node could be, for example, let's say 2. Then similarly, this will become the input. And then it will learn to predict based on this. Let's say next node is 3, similarly 5, and then 1. Okay. So you can see even the optimization problem can be set up as a large language model autoregressive prediction problem. Okay. Instead of predicting the next node, what are we learning? To instead of the next word, we're learning to predict the next node, right? Of course, the only difference is how will we feed it the graph? Okay, in case of NLP, how do we feed the input data to it? Okay, let's say our input prompt is, hello there, how are you? And we, based on this, we wanted to generate some next set of words. So if this is the input, how will we feed this to our model? As we discussed, what will we do to hello? Somehow convert it to set of numbers, a vector. If we decided on embedding size of 512 by 1, each word will be converted to 512 by 1, and so on, right? So now let me see if some of you can think about a good solution. We want to input the graph as a set of vectors, okay? So what will we, how, is there a possibility somehow we can model it like NLP set of vectors represent, see, instead of word, what is the equivalent over here in our problem? node. Okay, so what if I create an initial vector? It will say the first entry over here will be node number, right? What else do what other information? Because I wanted to understand the graph. Suppose in an XY coordinate system, the X coordinate of this node is, let's say, 23, Y coordinate is 17. So can I put the X coordinate and Y coordinate of whatever this first node is? Okay. Is that enough, or do I need to give it some more information? Distance between the nodes. Exactly right. So see, it needs to know the whole graph, because otherwise it will not be able to learn what should be the optimal tour, right? So as you can see, sure, we should give it, if the distance between 1 to 2 is 12, next number should be 12. If the distance between one, because it needs to know how is one related to all the other nodes. So we can go 1 to 12, 1 to, which is this one, right? Let's say 1 to 3 is 21. So then next number will be 21. Let's say 1 to 4 is 17. So next number will be 17. Let's say 1 to 5 is 9. So you can see this is how the input will be for the first node. And now you get the idea. How about the second node? Okay, node number will be 2, whatever the XY coordinate is, and whatever the distances are to the other 4 nodes from node number 2, right? If I had total 5 nodes in my system, I can create these vectors, right? So for those of you who took the NLP course, remember our starting point was what? Okay, so our starting point was if this is the input we wanted to feed to our transformer, right? We had a dictionary in the beginning. We created a dictionary of unique words like apple, whatever, azure, okay, zebra. So let's pretend in our dictionary we have 50,000 words. Okay. And let's pretend hello appears in position number 817. Okay. So remember, what did we do? How did we convert this hello to 512 by 1 vector? We created a simple neural network. And if the goal is to convert it to 512 numbers, how many neurons will we pick in our embedding network? Each neuron outputs 1 number, right? So if the goal is convert this hello to 512 numbers, how many neurons will we pick? 512. So this way we will get 512 numbers. And we want to convert hello, right? Hello is appearing at position number 817 in our dictionary of 50,000 words. So what will we do? We will create 50,000 numbers. Everywhere it will be a 0, except in position 817, there will be a 1. And all these 50,000 numbers will be fed to our neural network, which will have a weight matrix over here. The weight matrix size will be 50,000 by 512. So we'll transform these 50,000 numbers into 512 numbers. And this is how we start out. Once we have the 512 numbers, we feed it to our transformer architecture. It processes, learns the representations, and produces the output, right? So coming to our setup over here, let's say now we wanted to solve the optimization problem, okay? And let's say for a simple 5-node problem. So my question is, what is our initial set of numbers over here? What's the size of this vector? Okay, remember first one was the node number, then X and Y, and then distance to the 4 remaining nodes. So total is what? 7 by 1, right? Okay, so because we want to use this, let's pretend the same LLM architecture where the embedding is 512 by 1. So how will I convert these set of 7 numbers to 512 by 1 so that I can go back to the same LLM transformer? What should I do? I'll give you a hint. I should create a simple neural network. How many neurons will be in that neural network? 512, okay? So it will produce, as you can see, 512 outputs. How many inputs will it have? 7, okay? So what will be the weight matrix then? 7 by 512. So this is what we call the embedding network that we will use to transform the TSP problem to the same domain as, or the same uh, style as the LLM is expecting the input to be. Now we can use the same transformer and have it learn the next node, okay? So as like I said, we'll feed in this data for the 5 nodes. And further, we will start out with node 1, and it will learn to predict node 4. Then based on that, it will learn to predict node 2, then node 3, then node 5, and then 1, okay? So my question is, if we generated in this autoregressive style, as you guys will also see in one of the assignments, you will see it works, okay? Does it give us the very optimal solution? Okay. And as you guys will discover, for small problems, meaning for small graphs, it does a beautiful job. But if I give it a 100-node problem, it does a decent job, but not the optimal solution, okay? Because as you can see, 100 factorial is such a huge space that it's not able to learn the optimal, right? Okay, again, going back to NLP, if you guys remember, one of the reasons the transformer works really well, and we'll go into the details of the transformer for the benefit of those of you who did not take the NLP course. But today, the goal is to give you an overview and motivation for this field. Uh, so we had talked about, not only just the transformer, but in deep learning, right? Or AI, how do these systems learn? Okay. And the answer is they learn from data. Okay. The more data we have, the better our learning will be. Okay. So in case of NLP, as we had discussed, the good news was the data is abundant, okay? We can go to any website, any book, textbook, any newspaper article, news article, sports article, okay? We just start collecting all this text, right? Like I said, even if it is hello there, how are you? Like something simple like this, we will just feed in hello there and have it learn how. Feed in hello there, how, learn R. So if you collected 100 words, doesn't matter from where, okay, you can use it to, out of it, you can create 99 training pairs because based on the first word over here, you will make it learn to predict the second word. Based on first two, you will make it learn to predict the third word. Based on first three, make it learn to predict the fourth. So out of 100 words, you can have it learn 99 times. So uh, uh, so in NLP, and that's why, like ChatGPT have been trained on trillions of data, okay, because data is easy, okay. So coming back to our optimization problem, okay, we also need data, okay. Okay, because if it doesn't have the data, how will it learn what is the optimal route, right? So to give you an example, let's say we started out with graph as the input. The graph can be converted to set of vectors as we just discussed, and then eventually converted to embedding, right? And then we start out with representation of node 1 as the start point. Based on this input, what will it learn to predict? For example, let's say the representation of node 4. Okay, let's pretend it predicted 4, right? And let's pretend somehow we know the optimal. Because for a 5-node problem, can we exhaustively examine all the 120 combinations and know what the optimal is? Yes, right? Let's say the optimal is 1, 3, 4, 2, 5, 1. Let's pretend this is the optimal tour. Okay, so as it generates 4 as the first output, okay, how will we make it learn? What should be the correct output? 3. So remember in deep learning, what do we do? How do we make the network learn? So let's refresh our memory. We create some kind of a deep network. Doesn't matter whether it's a transformer or a CNN. Okay, then it will have some classifier at the output. Okay, for our 5-node problem, can you guys guess how many outputs will this classifier have? 5. Okay. How will we know what is it predicting? Like I said, we said it predicted 4. So we feed in the graph. So we feed in all of this as the input. Okay, and I'm saying the network predicted 4. How will we know that it is by looking at these 5 outputs that it's predicting 4? Remember, what do we do at the very end? If we wanted the network, if we are doing a classification type of problem, we want one answer out of it. We put a softmax at the end, right? And softmax will produce some numbers, let's say 0.02, 0.13. The sum of these numbers will be 1. Remember, that's a property of the softmax. It converts it to what we call a probability distribution, right? And let's say this is 0.27, and let's say this is 0.41. So 68, 81, 83. So if I calculated it correctly, sum should be 1. Okay, so let's say this is how it came out. Okay. So if these were the numbers produced based on a given 5-node graph to our deep network, by looking at these numbers, which output is it predicting? Which node is it predicting? 4. Because if you take a look, this is position 1, 2, 3, 4, which is the highest. Whatever is the highest number, that's what our network predicts, right? Okay, so it's predicting in this example 4. So this is what it predicted. But based on our training data, what was the correct output? 3. Okay, so then remember, what do we do over here? whatever outputs we obtain, we further feed it to loss function. The output of a loss function is always a scalar, meaning one number. Okay. Based on the loss function, we will go back and we try to minimize the loss and we adjust weights so that next time it will not produce 4 as the correct answer. And hopefully with more and more training, it will learn to predict 3. Okay. So what kind of loss function we use when we have a multi-class classification? Anybody remembers from previous deep learning courses? Cross entropy loss. Okay. So our large language models, if we go back, also, if you remember, for those of you who took the NLP course, they were using cross entropy loss at the very end, then going back and adjusting the weights. Okay. So anyway, coming back to RL, what I'm trying to say is this is how we can train it. Let's pretend somehow we have the optimal data. For a 5-node problem, it's easy to generate. What if we have a 100-node problem? Okay, we cannot go and how do we create the training data is the question. Because if we don't have training data, we cannot make our network learn. Okay. The answer is if we have a large node problem, we cannot get the optimal always, but we can get near optimal. There are a lot of algorithms that have been developed where very quickly they will give you close to optimal solution. Okay, so in this case, for example, one of those algorithms is called Concord. One of my PhD students and I developed a parallel end colony optimization. And we also get pretty quickly close to optimal solution. So anyway, using one of these algorithms, we can generate the training data even if the number of nodes is 100 or larger. Okay, so we now can go back, keep repeating this process on the training data, keep having it learn and learn. And then now we can give it an unknown 100-node graph and have it generate the output. Okay. So here's the interesting part from research point of view. All of these near optimal solutions to combinatorial optimization problems, for example, the N colony, some of you might have heard of these genetic algorithms. There's another type of algorithm called simulated annealing. Okay, so all of these are combinatorial optimization problems. They don't give us the optimal solution. For small instances, they'll give us the optimal solution, but for large instances, they come close. Okay. Anyway, all of these are iterative algorithms. Meaning what they do is they gradually refine the output, and we have to repeat it thousands of times. It keeps refining whatever the optimization it was doing until it comes close to a near optimal solution, right? And remember, our curiosity is all of you are here very interested in AI. Hopefully, that's why you're taking the course. Okay, so the question is this real AI or is it just memorizing from a lot of the data that we are feeding it? Okay, and I know Scott and I had many discussions related to this. So, and one of the reasons I wanted to study the combinatorial optimization problem is because it is NP hard problem. Nobody has ever been able to solve it in the entire history of computing, meaning optimally solve it. Okay. Can LLMs give us the optimal solution in one shot without having to go through and refine and refine and refine, right? Meaning, coming back over here, like I said, it will, can we make it learn? Like I was giving you the example over here, start from node 1, predict 4, then based on 4, predict 2, then 3, then 5, then 1, then it's done. Okay, we don't have to go back and have it refine it, right? If you take a look at this 100 factorial dimensional space, it is very, very complex. Okay, can LLMs see through this vast space and tell us this is the optimal? Okay, so that's our goal. Okay, and with all of your brain power and us, we will see if we can come closer, right? So with my PhD student, we have come close, but we haven't solved it yet. Okay, uh, now, so once again, coming back to the motivation for reinforcement learning, LLM, how do we train it? To two-step process, right? What was the first step? To predict. Next word, right? Okay. In our TSP problem, what did I say? It will predict next node. But if it only fixes on the next node, right? Will it be able to see the global landscape? Meaning, because our interest in optimal solution. Okay. So going back to LLMs, after we make it learn to predict the next word, how do we make it even better? As I mentioned, nobody will be using ChatGPT if this step was not there, because the outputs will be totally disjointed. It will be hardly of any use to us. It's the RLHF which makes it very human-like. We can have a conversation with it. It can go back and relate to the context. So think of this reinforcement learning, that it, as I mentioned in the beginning of the lecture, it takes a look at not just the next part, but globally as we are going through the whole flow, the entire generation. Is there a cohesiveness in the entire generation or not? Okay, so coming back to over here, suppose we make it learn to predict the next node, and let's pretend it works 90% of the time, or within 10%, it's close to the optimal solution, but not the optimal solution. How could we make it even better? Let's apply the same concept as we did in LLMs. Okay, meaning let's take a look at the entire flow that it has created, entire path that it has created, and compute the cost of this. And just like, we have a preference. Remember, RLHF is based on preference data. Okay, if it generates two outputs, we tell it which one is better, so that it goes back and makes our networks. Okay, so let's say for the same input, it generated two solutions. Okay, one is better than the other. If we can translate that to a different loss function, which as you guys will learn in this course, this DPO, direct preference optimization, is a loss function that we will create, which will learn from the preferences, so that based on the two different outputs that are possible, it will go back and gradually tune this output generation to favor the one which is more beneficial to us. Okay. So the question is, let me see if you can understand this. Let's go to the LLM example. Okay, how did we generate the data for RLHF? Remember, here we need preference data. Okay, and if you recall, what did I say? How do we train ChatGPT? We have it generate one response corresponding to a prompt. Okay, then we say regenerate. For the same prompt, it generates a second response, right? Because this is what you guys have experienced when we go to ChatGPT and have it regenerate. Then what do? Then it asks us, which one do we prefer? Okay. So this is how the preference data is collected based on human feedback. Okay. My question to you is, if we wanted to now go to the TSP domain, combinatorial optimization domain, is there a way for us to create preference data? Do we have to ask a human? Here's the node sequence, you generated. Okay. And let's say there's another sequence, 1, 4, 3, 2, 5, 1. Okay. Do we need a human to tell us one is better than the other? Yes or no?
No.
And why not? We already know the graph. We can plug in our graph, this one. We can plug in this one. In fact, even better. Okay. Let's go to the 5-node problem. And let me go back to this example over here. We trained our network using the next node prediction. And where did we get the optimal data? Optimal data, let's pretend we use the parallel n colony optimization or the Concord algorithm, which is standard available, to generate the optimal data. We kept training it on this next node prediction until it became fairly decent, right? We give it now one graph as the input. Okay, and let's say for this graph, let's pick the 5-node problem. It generates 1, 4, 5, 3, 2, 1. Okay, so this is the generated output. Okay, do we know the optimal for this graph? Yeah, from Concord, we know the optimal. So let's say this is the optimal. From a preference point of view, which is preferred? Optimal. So we don't even have to do anything. We simply ask it, okay, tell us what you are generating. And we know the optimal. We say, okay, here's the loss function in terms of preference between the optimal and this. Okay, so remember, this will not be cross entropy. This will be a different loss function. Now go back, adjust the weights, so you become even better, okay? So anyway, as we go along, we'll do this together, we will do this. And so main point I'm trying to make is that in the world of AI, as of now, okay, ChatGPT will not exist if it was not up to reinforcement learning, okay? The learning of these AI models, the most sophisticated models like ChatGPT, is a two-step process. First, learn to predict the next word or the next node or next token or whatever, right? After it has learned that, then we also make it learn we take a look at the global picture. Okay, tell us the entire response. And we say, okay, no, it could be made better. Here's a better response. Go back and tune your weights so that now you are favoring even the next word prediction to become more tuned to how we like it to be. Okay. In case of human text, it is subjective to our human bias. Okay. But for some of the problems, as I gave you an example of a combinatorial optimization, there is no bias involved. There's an absolute, this is better than what you generated, go and learn. Okay. So to me, it would be amazing if we can show the entire field of computer science will, be thrown out because there's a whole, theoretical computer science which focuses on, these NP hard problems. And if we can say, hey, LLM can spit it out the solution, you don't need to recycle, iterate through the solution. Okay. I don't know whether that's possible or not, but in our initial work, we have shown we're coming close. And we only use 50,000 training data. If you take a look at ChatGPT, it uses trillions of data. So had we used that, could it really solve 100 factorial problem in an instant? So that would be pretty amazing. So anyway, all I'm saying is in the world of technology, in the world of AI, and now quantum, okay, some really neat things are very, very exciting from learning point of view. So I hope you guys have your curiosity and your interest, and it is really amazing to see how where the human intelligence is moving forward. Okay. So anyway, so let me give you a tiny bit idea of RL a little bit more. Then I'll stop today. Today is just an overview, and then we'll go into the real stuff. And once again, we'll start from the very basics and go to the advanced. Another thing I'll mention is with anything, right? I strongly believe if your foundation is weak, then whatever you learn is superficial, okay? Meaning you can understand it. Maybe you can use a library, have it generate something, but you cannot improve the state of the art if you do not really understand how it works, right? And the foundation, as we went through in previous courses as well, regardless if it was deep learning or large language models, sometimes require a little bit of math, a little bit of statistics, okay, probability, and same thing in RL. Okay, the foundation of RL is based on some real, very, very interesting, there's a concept given to us by Bellman equations. The whole learning in RL is based on his foundational theory. So what that is, and so I will be reviewing a little bit of statistics and probability and math related to, so that we understand this foundation nicely. For those of you who say, oh, I don't have a strong math background, I again will say, don't worry it's not that I'm asking you to learn to write these equations. And, our goal is really to understand the high level view behind these equations, okay? So you won't be asked on the exam, show me, calculate these equations, or, nothing like that. But if we can get a high level intuition, what is the meaning behind this math, which I'll be able to simplify it and give it to you. So at least try to understand. So first couple of lectures, even if they are a little not as exciting, because, math is in the beginning is a little bit boring. But keep reminding yourself the fun part is coming, because we'll be taking a look at real practical examples. But without the foundation, our later would not be meaningful. So So let me go 5 more minutes. Hey, as you guys know, all lectures will be recorded. So the website for the course is http kiwi.bridgeport.edu, followed by name of the course, which is CPG 591, no spaces, and UB student and UB student 2022, same as you did in the previous deep learning web or any of the courses, okay? Um, right now, if you go there, the last time when I taught this course, the lectures are there. Okay, of course, this time we'll make it, for example, last time we did not cover direct preference optimization. So there's more current research that has been done. So I'll introduce some more recent research papers as well. Uh, so we'll improve the course, more examples, more assignments. And let me take you to the course a little bit, course website. Okay, so this is what it looks like, reinforcement learning. Okay, for example, if I take you to the handouts, I'll be adding some more as we go along, right? Lecture one handout is, as you can see, based on some of the probability and statistics and whatever concepts we'll be needing. Okay. So for example, if I go over here, so course overview, like I said, we'll be taking a look at different reinforcement learning algorithms, starting from the foundation given to us by Bellman. Okay. And to understand the Bellman equations, as I will quickly show you, we will need the concept of PDF, joint PDF, mutual information, conditional probability, expectation, marginalization, and Bayes theorem. Again, I'll explain it in a very, very simple manner. So don't worry if don't be intimidated by these terms. They all have a very, very simple, easy to understand meaning behind them. Okay. Uh, So our goal is, cover the latest developments in reinforcement learning. We want to be able to see the latest research papers and top our AI conferences. Okay. And slight challenge over here is, like I said, in the beginning. Okay. The math is a little bit intimidating in the beginning. But once we understand the big idea or the motivation behind it, it's really very commonsensical. Okay. Of course, we'll have to program. Then, only we see the benefit of all of these. If we simply talk about it and don't do anything, the learning is not complete, right? So anyway, now let me give you tiny bit introduction to just 2-minute introduction, and we'll go into the details next time. Okay. So unlike previous courses, deep learning or NLP, right, where the data is more well-defined, here, one of the challenges of some of the reinforcement learning, not all of it, is that we deal with a changing or a dynamic environment. Okay, so let me give you an example of a self-driving car. Okay, so if you take a look at this picture, this part over here, so this part over here is our deep network. And this is what we will be creating. This is what we'll be learning, right? And if you remember from our previous courses, what does theta indicate? Anybody remembers? Okay, theta is the weights and biases or the parameters of the network, which in the beginning are randomly initialized. Through training, it will adjust those weights and biases so that it learns to do its job, right? Okay, so the weights and biases of all of these deep network is theta. Okay, now if you take a look over here, there's some conditional probability given over here. Pi theta A given S. Okay, so let me try to explain this. What does that mean in plain English? Okay, so let's say we have a network, some deep network that we created. Okay, as we discussed in the output, what do we typically put over here? Classifier, right? The classifier is typically a two-layer network, correct? And in the very last layer, what type of math function that we use before we produce the output? Softmax, very good. And what does the softmax do? Converts the output to probability distribution. Whenever we say probability distribution, what does that mean? All that means is we are outputting numbers, and some of those numbers will be 1, okay? So that you can take a look at any output and you will know. So as a percentage, what is the probability of that being selected, right? So if one of the outputs is 0.05, that means there's a 5% probability this will be the output, okay? So anyway, output is a probability distribution with a softmax, right? So in RL terminology, like in every field, there's some terminology, right? So in RL terminology, the output is often referred to as pi, okay? Pi means policy because the job of this deep network is to make a decision. Okay, for example, if this is controlling a self-driving car, it has to decide, should it accelerate? Should it turn left? Should it turn right? Should it stop? Okay, so that policy is basically its decision-making capability. Okay, so if one of the outputs says turn left, one of the outputs says turn right, one of the outputs says stop or accelerate, right? So each one of them has a certain probability. And input, as you can see, are basically the road conditions. Okay, so there might be a camera feeding to our deep network model in a self-driving car situation. Based on the road conditions, this classifier, like I said, will decide what should the car do, right? So the output over here, we represent in the terminology pi. And now hopefully you'll be able to understand it has to take an action, right? A is for action. Like I said, action could be turn left, turn right, stop, accelerate, whatever. Okay. But for it to take an action, what is the criteria it has to use? It has to, based on the road conditions, right? Which we refer in the RL terminology as the state. Okay, what state are we in? Based on that state, we will take an action. So now hopefully this will make sense. So how do we read it? Okay, pi, like I said, is the output. Output is the action. In the probability terminology, this vertical bar means given. So given a state, what is the action we should take? Okay, each action has a certain probability. And so, for example, if this is the probability of stopping, pi a given s will be 0.5 in this example, okay, for stopping, okay. Now, whatever action we take, remember, is decided by this network. the weights and biases of this network are represented by what? Theta. So if I have to define what is going on over here in this whole system, I can say it's deciding what action to take based on what state we are in. And the action is decided by our network, which has parameters theta, weights and biases. Okay. So mathematically, this pi theta A given S is basically this diagram. Okay. So we'll be going over this so many times that by the 2-3 lectures, you'll be fluent in it. If I draw something, you'll be immediately, I mean, if I write something mathematically, you'll be able to see, oh, yeah, it's pretty easy. This is what we mean, okay? You know, some of you, for example, you remember some of you were in the 501 design patterns class, and I was saying the same thing. If I show you the code, you'll become totally confused. But if I draw the diagram, it's easy, right? So here, the goal is we should be able to relate the math to what are we doing. Okay, so now let's go back to the diagram. Okay, so does this make sense now? Pi theta A given S, which means our network will be deciding what action to take, right? And again, and think of easy example like a self-driving car, whether we are accelerating, stopping, turning left, turning right, right? Okay, for this action to be proper, what is it going to base it on? State. So the state becomes the input to our network. Okay, whether that's an image or whether it's sensors that we put in a robotic system, whatever the case may be. Okay, so as we take the action, right? Because remember, if we are driving, let's say this is our car. Okay, there are cars in front. So if we accelerate, we may become closer to the next car. So you can see the state changes. State is how are we with respect to the rest of our environment. Okay, so S prime in our RL terminology basically means, hard to write over here, next state. Okay, because we took an action, right? Let's say we accelerated. We became closer to the next car. So the state has changed for the whole system. Okay, so we write it as P of, okay, P is the probability of S prime. S prime is the next state. And what was the next state based on? Current state and what? And the action, because we accelerated, right? Or we stopped, whatever the case may be. So S prime becomes the next state. So this S prime, as you can see, will go back. And this S prime will now become S. So that based on this new state, what should be the next action, right? So an RL system, I gave you the example of the traveling salesman problem, which was in a fixed environment. Typically, one of the applications of RL is in robotics or in self-driving cars, where whatever we are interacting with is continuously changing. We apply an action to our robot or our car, and that changes and becomes S prime. We go back based on this new state, we apply another action, and we are continuously interacting with the environment, right? Okay, so the question now is, in this scenario, how does the system learn? Okay, in all the examples I gave in today's overview, we needed a training data where we knew what the optimal is, or we knew what output should be produced. For example, in a large language model, we know what should be the next word so that we can go back and adjust the weights. In this scenario, how does it learn? What is the training data? What is it supposed to follow? Okay. And the answer is in a RL system where robotics is involved or self-driving cars are involved, we train it not on uh, an optimal data, but we train it on a reward system. So we have concept of rewards. Uh, a reward could be positive. For example, if your car gets into an accident, that's a negative reward. Okay. Uh, if you take a look over here, let's see if we can understand this equation. I'll go over these equations again next time also, but let me see if, okay. What does this symbol mean? Sum, right? Add up everything up, right? And what are we adding? R. R is the reward. For example, let's say if you are driving successfully, your reward is positive. If you get into an accident, your reward is negative. If a lot of people are honking at you, uh, that's a negative reward. Okay. So what does the reward depend on? It depends on what state we are in and what action did we take, right? So if you are accelerating and getting to the tail of somebody else and driving, that's not a good thing. Okay, so the reward will be less. Okay, so the goal of RL is to remember we are summing all the rewards as we drive, because let's say as we are driving, there are 100 states involved every 1 second or every 1 millisecond or 1,000 states involved. So we are summing it over 1,000. Okay. So is the goal to reduce this term or get as high of a reward as possible? As high of a reward. We don't want our system to be crashing, which will be the case if we're getting negative rewards. So goal of RL is to maximize the rewards. Okay. And remember, what is our network learning? Our network is learning to take the proper action, right? Which is the policy or which is the probability in our softmax output. So as you can see, in this action that we are learning is based on what are the values of the weights and biases, right? So what this equation is saying is argmax of theta. Theta star means this is the best network that we have learned. It is the maximum of all. So if there were many weights and biases that were possible, whichever gives us the highest reward, that is the best network. So that is the meaning of this second equation over here. Next time, as I go through a little bit of the probability theory, you'll be able to understand this equation very nicely. Okay, like I said, all of these have very simplistic meanings to them. And from our learning point of view, let me just quickly mention this. Hey, the foundation of entire RL, this learning to maximize the reward, like I said, is based on Bellman equations. Okay, so in the beginning, they look a little bit intimidating. You'll see a lot of summations and conditional probabilities showing up. Don't worry about it. As I explain each step, the final step is what we will be programming. But we need to have a intuitive understanding of it. What is it doing? What's the purpose behind it? So we'll go through a little bit of this math so that we have a clear insight into the motivation behind how is it learning? What is the approach followed by the system, right? Okay, so anyway, to summarize, RL is a very, very important field of AI. As I mentioned, ChatGPT will not be ChatGPT if it's not for RL. Not only in ChatGPT scenarios, meaning large language model scenarios, in the robotics, which I truly believe is going to be the next revolution, is without RL, the robotics will not be robotics. Okay. So it's an important field. We'll have very good learning in it, a lot of fun. First part is a little bit of math, but don't worry, it does become very practical as we go along. So stay with it, keep learning, and we'll have a fun course. Okay, I'll stop here. Okay, so once again, the code for today is 6807, and all right. So in the last lecture, we developed a motivation for our reinforcement learning. And reinforcement learning is another type of deep learning. So as we had talked about in the previous lecture, the field of deep learning, which essentially is learning from data, goes into a few different categories. Of course, we have supervised learning, where, for example, we create CNNs or regular neural networks, and lately transformers, and also state space models. So these are some of the actual architectures, actual deep networks that we create. And then we train them based on some data. So in supervised learning, we are given some inputs, or in our typical terminology, X is our set of inputs. And then we have some Y, which is our expected outputs. And based on that, so our general philosophy, as you already know, just to very quickly give you, so we'll feed in X to our some model that we have created. This could be a CNN or a transformer or state space model, whatever. It will produce some outputs over here. Okay, whatever outputs it produces, we'll compare it to the expected outputs. In supervised learning, we have to know this. Otherwise, the network wouldn't know what to do. And then we create some kind of a loss function. The idea is this loss function will try to make this output as close to the expected output. Loss is always a scalar, like a number, right? The parameters of the model in our mathematical terminology, we denoted by theta, which is our weights and biases or whatever, based on whatever type of network it is, whatever the parameters of the models are. So the idea is we will feed in some training data. So this is some training data. Okay, for this training data, we already know the expected output. So in the beginning, the output it produces obviously will be far different from the expected output. Loss will be higher. So the whole idea is, if this is the landscape of the loss, these are our parameters over here, even though I'm drawing it in a single dimensional or 2D space. these could be in the millions or billions or trillions of parameters, especially with large language models. So we start out with random parameters and gradually we reduce the loss so that ideally we'd like to come up to the minimal loss. And at that time, the hope is whatever input we give it, it will produce an output very, very close to the expected output, right? So that is the supervised learning, regardless we are using NLP, we are applying to NLP, or regardless we are applying to vision problems, images, audio, video, whatever, right? So this is what we have learned in our previous courses, such as deep learning, advanced deep learning, natural language processing, right? So as we discussed in the previous lecture, if we take a look at LLM, right, which basically learns to predict the next token. So predict next token. Or a token could be a word. Typically, it's a subword. So based on an input sequence, for example, hello there, how are you? Today is going to be, and then it will learn to predict great. So if we say, hello there, how are you? Today is going to be great as the input, it will learn to predict day, right? So one at a time, it keeps learning to produce the next word, which we represent as a token based on our dictionary, right? Okay, so if we just train the LLM just to learn to predict the next token, as we discuss, whatever outputs it's producing, they may be okay, but if we are producing a lot of outputs, having it write an essay, the different sentences or the different paragraphs will not be coordinated with each other. They won't be a good flow. So to overcome these, LLMs do a two-step training process. Step one is the next state prediction or next token prediction. And step two is now to make the entire output as cohesive as possible, okay? So make entire sequence that it has generated, because see, next token is one, right? So make entire sequence cohesive. So here, this is where the RL or the reinforcement learning comes into play. Okay, so that is the motivation that we developed in our previous lecture. Okay, so the question is, how do we focus on the entire sequence? How does it learn from it, right? So in general, as we discussed, now coming to RL, RL learns to create an entire episode. Okay, as rewardful or as useful or as good as possible in case of writing. Okay, so RL could be applied to NLP, it could be applied to robotics, it could be applied to self-driving cars, and so on, right? So even though there will be a few variations of how we make it learn, right? But the fundamental idea is we will again have a model. Okay, model only produces one output. Okay, so for example, if you're driving, in case of a self-driving car, at a particular point in time, if the car is over here, either it has to accelerate or slow down or change lanes or whatever the case may be. So you can see this is the action it's going to take. So the output is the action. What's the input in case of RL? Input is where are we? What are we seeing, right? And we refer to that as the state. So based on a given state, our model, our AI model, will produce an output, which is what action it's supposed to take, right? Okay, now as we take the action, for example, we turn to a different lane as an example, you can see the state has changed, okay? What if we run into an accident? We try to change the lanes, there was already a car over there, right? So with every action and with every state that we take, there's a reward associated with it. Okay. Reward could be zero. Reward could be positive. Reward could be negative. For example, if there's, in case of a self-driving car, um, you did not do anything, you're just driving at a normal speed, so reward is zero. On the other hand, maybe speed limit was, let's say 25. Currently you are 20. From 20, you went to 25. You are now reducing the time it will take you to get to the destination. So we may decide, okay, in this case, we'll give you a reward of 10 points. Okay. On the other hand, you tried to change the lane. There was some other car over here. You got into an accident. Reward may be a -1,000, right? Okay. So the idea in RL is we take a look at, like I said, even though we are going step by step, meaning producing one output at a time, but we take a look at the entire episode. Episode is from start to finish. Okay, we may be taking, let's say, 200 actions over here, depending upon where we are applying the RL. We may be taking 5,000 actions. Like I said, as we are going through, we are accumulating rewards. So there's a reward over here, let's call it R1. There's a reward over here, let's call it R2. And similarly, R whatever 200. Okay, so as you can see, because the focus is to, just like I mentioned in case of a large language model, whatever it's producing, if it wrote an entire paragraph, we want to see what is the quality of writing? Are the sentences cohesive or not? So from a goal point of view, what we will do is we will just do R1 plus R2 plus R200, and that is our cumulative reward. Okay, so from a learning point of view, we want to, if I have to give you a high level goal of, what is it, in the beginning, this AI model again will have some parameters called theta, weights and biases, right? Which will be randomly initialized. So of course, if it's a self-driving car, it will perform terribly, get into accidents, not even get to the destination, right? So as you can see, what we are trying to do is have some kind of an idea of a total reward over here. Okay, because we want to get to the destination in as short of a time as possible by following all the rules. That's our goal. And that goal, as you will see, will be described in terms of the total reward. Okay, so if we have to say what is the goal of RL, in plain English, goal of RL is to create a model. Okay, such that the actions it produces result in, okay, small reward or high reward? High reward. Okay, Um, so from learning point of view, as you can see, unlike the supervised models that we are used to, where we go have our training data, there is no training data over here. Okay, we'll simply create a car, let it run into accidents, of course, in a simulated environment, not in a real environment. Okay, and keep having it so in the beginning, the reward will be very small, right? So we will go back over here and, just like based on the loss, we go back and adjust the weights in this case, uh, end goal would be go back, adjust the weights. So that eventually these rewards keep increasing and they become as high as possible, right? Okay, so keep in mind, rewards are an indirect product. It's not like the network. The network, what does it produce? The AI model, it simply produces an action, okay, which further leads to a reward. Uh, so uh, so once again, the difficulty, or I shouldn't say difficulty, or the difference over here compared to traditional deep learning is having clarity in our mind. How are we going to make it learn? Okay. Um, so there's just like in the deep learning world. So if we go to the traditional deep learning, and then I'll contrast it with our RL. Okay, let's say we have some model, so some deep network. Okay, we will give it some training data, feed the input, it will produce some outputs, right? Then we will have some target outputs or expected outputs. Based on these, as we just discussed, we'll create some kind of a loss function. Okay, if there's more than one output, okay, then as you know from your deep learning knowledge, what is a good loss function? No, softmax is just converting the outputs to a probability distribution, right? Okay, so cross entropy is the best loss function. All LLMs, as you have seen, for those of you who took the NLP class, we apply the cross entropy over here, which basically is something minus AI log of, log of AI, and this is our target YI, and we sum over all the outputs, right? Okay, so this is our, and there's a negative sign over here. So this is what the cross entropy loss is, and we try to minimize it. And so how do we adjust the parameters over here? We adjust the parameters theta minus lambda as our learning rate, right? Partial L over partial theta. So this is our stochastic gradient descent algorithm that we apply repeatedly by stochastically, meaning we don't pick the training data in a particular order. Every time we go through an epoch, we pick different sets of inputs so that it generalizes better. And once it has been trained on the unknown data, it will perform a lot better, right? Okay, so just like there was a concept over here that you guys learned, partial L over partial W1, partial L over partial B1, partial L over. I remember in the beginning of the deep learning course, we went through, learned how to compute all these derivatives so that we can update these parameters for, make it W1 equal to W1 minus lambda partial L over partial W1 and so on, right? So after we understood how we can make this loss smaller, how to adjust these weights, all these weights and biases. Eventually, it will learn very nicely from the data and perform very well, right? So same way, the question is for our, now let's go to the RL scenario. RL scenario, we will again have a deep network, which is initialized randomly in the beginning. Okay, it will have some outputs which translate to an action. Okay, so again, for example, for a self-driving car, there could be 10 outputs over here: accelerate, go left, go right, speed up or whatever, right? Hold constant speed, whatever, right? So, so if there were 10 outputs over here, okay, how will we know which action are we going to take? We can take the softmax, whichever is the highest output, that would be the action we'll be taking, right? Okay, so anyway, as we discussed, this will indirectly translate to some kind of a reward. And then somehow we have to go back now based on the reward, not based on the loss, because now we want to maximize the rewards. We have to go and adjust the weights, right? So again, we need some kind of a theory, theoretical foundations, so that once we know that this will eventually keep adjusting its weights, so that rewards keep getting better and better, right? Okay, so there's a beautiful theory that was proposed by Bellman to precisely help us understand how do we set up the problem mathematically, which will end to higher rewards. Okay, so in my opinion, just like for some of you in computer science, as I have mentioned, when you take the CPSC 501 class, you cannot call yourself a computer scientist if you do not know algorithms and do not know design patterns in object-oriented programming, right? Because those are the foundations of software development, right? Very similarly, even though you can do RL without even understanding Bellman equations, okay, you cannot call yourself an expert in RL if you do not have a good understanding of the Bellman equations, right? Okay, in the beginning, they're a little bit intimidating. They involve some probability statistics concepts, okay? But my goal is to simplify them, see without, being intimidated by these equations, if we can get a high-level idea what is exactly it's trying to do, right? And as you will see, high-level idea is extremely, extremely simple, okay? Uh, so like I always say, if you have a strong foundation, the most difficult things in that field will become easy, okay? So today's lecture will be focusing on understanding the Bellman equations, which is the whole foundation of RL, okay? So before I show you the Bellman equations, what we will do is I'll quickly review some fundamental probability and statistics with you. Okay, most of you hopefully already know this, but even if you don't, as you will see, again, I won't be asking you to derive these equations. We just want to have an understanding so that as we go and implement RL, we know what we are doing, how statistically or probabilistically it is giving us an answer which will keep getting to a higher and higher reward, right? Okay, so I'll take you to our course website, which hopefully all of you have received uh, the URL, which is http kiwi.bridgeport.edu/course number CPG 591 UB student 2022, right? So let me take you to the website. Okay, if you go to the website, you will see under the handouts, there are a few handouts already there, okay? Last time I taught it, these handouts were there. If we need any more new handouts, I'll add those. Okay, so you will see lecture one, handout probability and statistics background. So let's take a quick look at it. Again, if you are coming from not as strong of a math background, do not worry. Our goal is simply to get a high level intuition of this math. Okay, so let's start. Okay, from understanding RL and implementing RL point of view, there's few concepts we need. One is the PDF, probability density function, joint PDF. When more than one random variable is involved, how they interact with each other, okay? Sometime later, we will need this concept called mutual information. And again, another very important part from RL point of view is conditional probability, the concept of expectation, marginalization, and the Bayes theorem, okay? And we'll be often dealing with some distributions. So having just an overall idea of what exactly is a distribution, right? So, so in my opinion, uh, math is very easy, especially the calculus one. Calculus is very easy because it has very simple rules. For example, if I gave you y equal to 3x squared plus 6x minus 7, and if I said, give me the derivative with respect to dx, right? Everybody knows, okay, bring it down, multiply it by 6, then reduce the power, so x squared will become x. So this was x1, it will become x0, which is 1. So answer is 6x minus 6. Sorry, plus 6, right? Okay, same way if you are doing an integral, easy, okay? The often, if we come to statistics as an example, so what exactly is a distribution? This is where a lot of students, you know, uh, because like a derivative, you know, if you're given a curve, right? So for example, at this point, what is this, the meaning of dy over dx? It's basically the slope. How fast is the data changing? That's all it's telling us, right? So in statistics, when we talk about distributions, okay, it is basically telling us it's not talking about one data item. Anytime we talk about statistics, that means we have many data items. And all we are saying is how they are distributed, meaning how are they clustered, okay? For example, easy example is let's take a look at our test scores. Okay, if you guys took a test, let's say there are 100 students in the class, okay, there will be a class average, right? So for example, let's say the average was 65, okay? So if we go from 60 to 70 and find out how many students, you know, some student may have a 63, 64, 67. So if we just simply count, so if we put the count over here on the y-axis, let's say out of 100 students, 40 had a score between 60 and 70, right? Similarly, we go between 50 and 60 and we find out maybe 30 students, maybe over here, another 32 students. Okay, that will exceed. Let me make it 20 and 22. Anyway, as we keep going to higher and higher, you'll see less number of students are within that range. Okay, so for example, 90 to 100 range, maybe there are 3 students only, right? So if we try to draw a curve on this one, you'll see it will follow like a bell-shaped curve. And so this is what we call Gaussian distribution. Okay, it turns out a lot of data in nature follows this Gaussian distribution. As you can see, the Gaussian distribution is characterized by 2 parameters. two main parameters. And what are those parameters? Which essentially describe the shape of this bell curve. See this bell curve? It could, if the could be very, meaning a lot of people are close to the mean, but very few are in the high range, very few are in the low range. So this could be the shape of the curve, or the shape of the curve could be something like this. Okay, it's more spread out. Okay. Um, so the two parameters which describe the shape of how the data is distributing, one is the mean, and the other is the standard deviation. Sorry, standard deviation. So, okay, which is often described by this symbol over here. So standard deviation tells us, for example, 66% of the entire data is typically within one standard deviation and 90% within two standard deviations and so on, right? Okay, so the exact shape of the bell curve could be x minus mu over sigma squares, and there's some term over here. So anyway, the exact formula looks like this. I'll show you the exact formula in a second, but that describes the shape of this bell curve depending upon the mu and sigma. Either the bell curve will be very close to, have a thin shape, or will be spread out shape, right? Okay, so this is in one dimension. Okay, so let me give you one more concept over here. Let's take a look at data for heights of males and females. Okay, so if we take a look at the data, right? Let's pretend this is the height over here. Okay, sorry, this is the count. And this is the height over here. Okay, so as we know, height of males is a little bit, males are taller than females, right? Let's pretend somewhere over here is the height of the males, and let's say average height is 5 feet, let's say 8 inches. Okay, that's the average. Okay, so as you will see, if we take a look at how many people, if we're, sample 1,000 people, as you will see, most of them will be centered around this uh, 5 feet 8 inch mean, right? Some will be very tall, some will be shorter, right? Okay. And very similarly, if let's pretend the height of females is somewhere over here, let's say 5 feet 4 inches is the average height of a female. So as you can see, there will be another bell curve over here, centered around over here. Are their means the same or different? See, this is mu1, this is different means, right? Same way, there might be small difference in their standard deviations as well. So they may have a different standard deviations, okay? So as you can see, this type of data is not one Gaussian. This is a mixture of Gaussian. So this type of data, if we try to represent by one Gaussian, it will not be an accurate representation of the data, right? So when we have a mixture of Gaussians, in this case, it's a mixture of two Gaussians. In some other domain, it might be mixture of 5 Gaussians, okay? Then we have a concept of likelihood, okay? Likelihood is not a probability. It's like a number, okay, which tells us how likely is it a given data belongs to a particular distribution? So how likely is that a given data belongs to a distribution? Okay, so for example, let's take a look at this example. Suppose we are given a person, we don't know if that's a female or a male, okay? And suppose the height of that person is 5 feet 6 inches, okay? So as you can see in my example, where is it? Exactly in the middle, okay? So can we tell whether that person is going to be a male or a female? Okay. And the answer is yes. This is where the calculation of likelihood comes into play. Okay. What we will do is remember each one of these curves is described by, let me just quickly put the formula over there, exact formula, so that I don't make a mistake. Okay, 1/2 sigma square pi. So this is the formula for the Gaussian distribution. So the formula is, like I said, 1/2 pi sigma square e to the x minus mu square over sigma. Was it sigma square or sigma? 2 sigma square. Okay. So like I said, what is mu over here? 5 feet 4 inches, right? Sigma, whatever is the based on these 1,000 observations, we know what it is, right? Same way over here, we have a mu and another formula over here. 1/2 pi sigma 2 square. Let me make it sigma 1, mu 1, right? And e to the x minus mu 2 divided by 2 sigma 2 square, right? Okay, so what we will do is if we are given a person, let's say whose height is 5 feet 6 inches, we'll plug it into this formula and we'll get a number, okay? Because all you're doing is this x becomes 5 feet 6 inches. Sigma 1 is already given to us based on our data for the 1,000. We know what the standard deviation is. We know the mean, right? So we'll get a number. Okay, and let's say the number is 2.31 once we plug this into the female curve. Okay. Similarly, we plug this into the formula for the male curve. We know mu 2 is 5 feet 8 inches, whatever the sigma 2 is. And let's say we get a number 2.29. Okay, so now can we tell what is the likelihood that this person is a male or a female? So you can see when we plugged it into the distribution for females, it produced a higher likelihood, right? So that's how statistically we decide. Again, this is just a likelihood. It doesn't mean it's guaranteed. Okay, but anyway, so to summarize, a lot of data follows a Gaussian distribution. Okay, we could have one Gaussian, or we could have a mixture of Gaussians. When we already know the distribution, then we go and for the unknown data, we can determine the likelihood of that belonging to one of the distributions, right? Okay, so coming back to our handout. Hey, so once again, probability distributions are how the data is clustering. Okay, in a Gaussian distribution, what does it do? It clusters very close to the mean. right? If I draw a 2D data, so all these example of height were one-dimensional, right? Same way we can have 2D data, 3D data, high-dimensional data. In a 2D data, again, there will be some mean. Okay, let's say the mean is over here. There will be some data. Let's pretend each dot is one data item. Okay, so as we go away from the mean, there will be less and less data. So it will follow sort of like a circular pattern over here. Uh, Same way if we go to 3D data, I'm not good at drawing 3D, but you can easily see it will make, again, a bell type of curve in 3 dimensions, like a real bell. Okay. Okay, so coming back to Okay, so as we have distributions, then the related, we talked about a single distribution, right? If we have multi-dimensions to it, then we are also interested in the joint distribution. So that is called the joint PDF. So let me go one step at a time. Okay, I'll come to this picture in a second. Okay, so now let's take a look at a good understanding of the joint PDF. Okay, uh, so just like, we talked about the PDF uh, for a single variable. Okay, suppose I call it f of x. X is, let's say, height of males or females. And as we discuss, this is represented as 2 pi sigma square, and then e to the x minus mu over 2 sigma square, right? So just like we have a PDF for a single variable. So this is for a single variable. Okay, sometimes we are interested in the PDF of multiple variables. How do they interact with each other in terms of the distribution or the clustering of the data, right? Okay, so this is where a lot of students get a little intimidated what's going on. So let me try to explain this through a very simple example. So I'll pick an example of 2 images. Pretend I1 is one image, I2 is another image, right? And remember, image is a collection of pixels like dots. Every dot can vary from 0 to 255. So if you take a look at this example, what I did is I assumed uh, this is a 4 by 4 pixel image, I1, 4 by 4 pixel image, I2, and the pixel values only vary from, let's say, they only can, even though in reality they will vary from 0 to 255. Here I picked easy numbers like 10, 20, 30, 40. Okay. Uh, so let's create first individual PDFs, meaning how is the data distributed within each image. Then we'll create a joint PDF so that we can see, is there a relationship, probabilistically speaking, between the 2 images, okay, between their pixels. So if you take a look at this curve, PDF phi1, just like in case of test score examples, remember we were counting how many students are between the range 60 to 70. And that's how we came up with the bell curve. How many students are between 70 to 80. So distribution is simply count of the data at a particular spot. Okay, that's what distribution is. So let's take a look at, if you take a look at PDF of I1, okay, because our pixels are only varying 10, 20, 30, 40, and 50. Okay, meaning those are the only values we put in our simple example. I don't need to worry about what if pixel value is 9, what if pixel value is 70, 80, 230, whatever, right? Okay, so let's take a look at how many times we see 10 in I1. Okay, so can you guys see what that is? There, you'll see a 10 over here, another 10 over here, another 10 over here. So 3. So what's the count? 3. And that's what distribution is. It's just the count of data at a particular spot. Okay, so take a look at for PDF of I1 for 10, what did I do? I put this 3 over there, right? This big dot over here, this one. Okay. Very similarly, now you can easily verify if you take a look at how many times 20 appeared in I1, 2, right? Let's go to 50. How many times do you see 50 over here? 1 is over here. Where do you see? Oh, yeah, same row. Okay, another 50 over here. So 2 times. So the count of this is 2, right? So this is not looking like a bell curve, but that's okay. Our distribution does not have to follow a bell curve. Only if we have large data, we see the Gaussian behavior. So in this case, it doesn't matter whatever that shape of for the distribution is. So anyway, that's PDF of I1. Very similarly, now can you verify very quickly? Let's pick one number. Let's take a look at 30. How many times 30 is appearing in I2? 1, 2, 3. So the count will be 3. So the y-axis is the count. How many times that data is appearing? Once again, that is the meaning of a distribution. Okay. So that's easy, right? We are taking a look at individual single variable distribution. Now let's take a look at joint PDF. How do I1 and I2 relate to each other from this distribution concept? Okay. So when we talk about the joint PDF of, we will write it as I1 and I2 together. So in our example, what numbers can I1 take? In this example, I1 can be 10, 20, 30, 40, or 50. What about I2? Same thing, right? So when we take a look, so by joint PDF, now what we will do is we'll take a look at the count for all possible combinations of each other, okay? Meaning, what if I1 is 10 and I2 is 10? How many times is that occurring? Okay, so here's the thing. When we take a look at I1 is 10, I2 is 10, it has to occur exactly in the same spot. We cannot just simply go to I2 and say, oh, I see 10 in another place. Okay, when the joint PDF comes, then a strong relationship appears. At the same point, is there also 10? So let's take a look at what will be PDF of I1 equal to 10, I2 equal to 10 from this data. So take a look, this 10 appears over here, right? So that will be 1, count of 1. Let's go another place where do you see 10? 10 is in this spot. Is it also 10 in I2 in the same spot? No, so then this doesn't contribute to the joint PDF. Okay, how about this one? So what will be PDF of 1010 then? 2. Okay, now you get the idea. So we'll compute PDF of 1020, 1030, 1040, 1050, then 2010, 2020, 2030, 2040, 2050. So you can see there will be 25 in this example, 25 combinations are possible for a particular value of I1, particular value of I2, and we can easily count in the exact same spot. So for example, let's do one more example of this. Let's see if everybody understands. So PDF of, let's pick 20 and 40. and tell me what that number is. So 20 appeared how many times in I1? 2, right? In the corresponding spot, there's no 40. So this will be 0. Okay, how about let's do one last example, PDF of 20 and 20. See this 20, there's another 20 over here in the same spot, so that will make it 1. Here's another 20 in the same spot, so we'll make it 2, right? So in the handout, if you go to the next page, you'll see the calculations for, do you see PDF of 2020, right? So it is 2 in this case, so we can do the calculations, right? Okay, so that's what join PDF is. Again, it's like a simple count. Okay. For discrete data, if in our example, this is discrete data, pixel values vary 0 through 255. Okay, so if we were looking at the real image, this will be 255 for one image are the possible values, or 256, 0 and 255 inclusive. So it will be 256 square counts that we will compute to be able to determine the joint PDF between two images. Okay, so joint PDF is straightforward, right? Later on, we will use one more concept, which is called the mutual information. Okay. So the idea is like this. Let's say we are given two images. Okay. Like I was saying, one option is let's compute the PDF of I1, I2. Okay. Once we have calculated, as you can see, it basically tells us what is the relationship between these two images. Like I said, if there's a certain value occurring over here, if at the exact same spot, the value is there, the count goes high, right? So you can think of it as this information can be used to determine the similarity between two images, right? Okay, it works, but the only problem is if there was even a slight shift of 1 pixel, okay, even though, so if I take the one image, this is 100% the same image, but let's say it's shifted by 1 pixel. What will happen to the joint PDF? It will produce a lot of zeros, right? Because nothing is matching. So joint PDF for similarity measure, maybe it's not as good of an idea. So this is where we use mutual information. Mutual information between, it doesn't have to be two images, it's between two distributions, is again a measure of similarity. So if two distributions are similar, then the similarity score will be higher. So sometimes we use this, particularly with images, mutual information is popular. So let me quickly show you what the formula is. Okay. The formula for case of images, you can see I have two summation signs. Why are they changing 0 to 255? Because in images, what do pixels vary? 0 to 255. So now this is the general formula. Okay, P of A of B times log of P of AB divided by P of A multiplied by P of B. Okay. For example, let's take a look for our example. What will be the mutual information? Mutual information will turn out to be a number. Okay, like I said, if we calculate this, this will give us an idea of the similarity. Higher this number, the more similar they are. Okay, so you can see over here, let's take a look at, for example, to okay, so for example, let me go to, okay, uh, so let's see when this is 10 and 10 as an example, right? So how many times, uh, so substitute A with I1, B with I2. So if we take a look at the count for I1 when the value is 10, uh, okay, so this will be two. Okay, let me just see, where did I get it? 3 P of A is 3. Okay, sorry, I need to go over here. Okay, so when I1 is 10, right? What's the count? 3. When I2 is 10, what's the count? 3, right? So, so this bottom part is when I1 is 10, I2 is 10. So you will see this will be 3 by 3, right? And this is the joint PDF. What is the joint PDF of 10 and 10? So if I go to my previous 10 and 10 is 2. So you can see over here, this part over here, 2 divided by 3 by 3 is coming for here for the 10-10 data, okay? Log, and the joint 10-10 is 2, as you saw previously, right? Similarly, you can sort of guess this would be for 10 and 20. So if we go, let's quickly verify. 10 and 20, for 10, it's 3. For 20, it is 2. What did I have there over here? I also have it for 3, 3. Okay. AB is 1. Okay, let me see which one did I do. Oh, I probably did it for this 1050 is 1 because all the others are 0. So 1020 does not make sense. We don't need to calculate because it's 0 anyway. So the next calculation I'm doing is where the joint PDF is non-zero, which is I1 of 10, I2 of 50. So if we go to 10 uh, is 3 and 50 is 3. So that's why we have, and the joint PDF 1050 is 1. So that's why you have over here join PDF 1050 is 1. So let me put it over here in case you view the lecture later. So this is basically PDF of 1050. So this is PDF of 10. And this is the individual PDF of 50, right? Okay, and remember this was the joint PDF, and this was the numerator was the same joint PDF. And PDF of 1050 was 1, so which is also this part over here, okay? So same way for all the non-zero values, you can go and calculate this out, and this will give you the mutual information, which once again is a statistical similarity between two images, and that's when we use. So down the road, if you are creating a new application, okay, and somebody says, oh, we are given two images, we want to determine some statistical similarity between them. Do we have a criteria for that? And like I said, one of the proven criterias for this is mutual information. There are others as well, but this is one of the popular ones, right? Okay, let's go back to our learning. So to summarize, what does the individual PDF do? It tells us how the data is distributed within one image as an example, or within one type of data. Could be test scores, could be height of males, whatever, right? And again, PDF is simply a count. Okay, and that's what we mean by distribution, right? Once we have individual distributions, sometimes we want to see what is the relationship between them, right? And that's where we come up with joint distributions, like you guys saw in this example. And all it does is pick certain value, okay, let's say V1 and V2. And then we say, how many times if I1 has this value V1, at the same spot, I2 has this the V2 value, then we increment the count. Okay. Uh, Meaning how will we compute the joint PDF? Like I said, for the height example, right? Let's say you are given some data for more, it will be clustered, let's say around 5 feet 4 inches. There will be more data for around 5 feet 8 inches, right? And you wanted to compute a joint PDF. Okay. For joint PDF, like I said, you'll pick a value. For example, let's say you pick 5 feet 3 inches for females, and let's say 5 feet, let's say also 5 feet 3 inches for males. Like I said, it's a for just like for two images, the data will be 256 squared, that many combinations, right? Okay, so let's say you find out for all the inches. No, the question is how we're going to know this. For example, the images, we know each pixel. So here we'll go into this full range, right? Let's say heights vary from 4 feet to 8 feet. Okay. You can discretize it, meaning you can say every 0.1 inch we will take a look and count. Or you can pick a range. I remember like our test scores, we said how many appear between 60 and 70 score, a range. Here also, we can say rather than going to, for example, we can say how many appear between 5 feet 2 inches and 5 feet 2.5 inches. Okay. And that count for a one particular value of female, then we'd say for the same case, what is the value? So let's say for this range, if we had a data for 1,000 population, for this range, we found there were 70 females. Okay. For the same range, now let's say for the exact same range, we found 50 males, right? So if we are creating a joint PDF, the number will be 120. Okay. But if we keep them separate, then each one has its own distribution. Okay. In the uniform distribution, the idea is that our data is spread out evenly. So there's no clustering that is appearing. So that is the uniform distribution. So for example, if we had 1,000 people, And let's pretend they are uniformly distributed between height of 4 feet to 8 feet. Okay. Then what will happen is maybe if we take a range of 4 to 4.05, 4.05 to 4.1, and so on, you'll see the count will be very close to each other. Maybe there will be 30 people, 30 people, 30 people. Okay, it may vary slightly, 29, 31. So if it is uniform, data is uniformly distributed, the count stays the same within that range, no matter where we go. Okay, but most data in nature follows the Gaussian distribution, meaning there's more data which is clustered here, less and less as we go away from the mean. Okay. Okay, so once again, don't be intimidated by distributions. They are simply telling us how the data as a count appears at a particular spot. Okay. Um, Okay, so now from RL point of view, we also need a good understanding of joint probability, conditional probability. You already got an idea of the joint distribution. Now we'll turn into probability. Uh, so there's a very famous theorem, which is called the Bayes theorem, that we'll be relying on to develop the foundation for RL. And the Bayes theorem goes like this: P of A given B, and I'll explain it by a simple example, equal to P of B given A, P of A divided by P of B. Okay. P of A given B multiplied by P of B is same as P of AB. So there's some, and similarly, P of B given A, P of A is also same as. Okay, when we write this comma, comma means and. Okay, so let's try to understand these relationships through a very simple example. Okay, let's say we have 100 students at UB. Okay, and let's say out of these 100 students, 60 are enrolled in CPEG 591, 40 are enrolled in our quantum class, CPEG 607. Okay, so if I draw like a diagram, suppose this is A. A is representing a CPG 591 student, okay? And B is representing a CPG 607 student. So, and let's pretend some students are taking both. So there are 20 students out of these 100 are taking both classes. Okay, so then this is our set B. And you can see the probability of a student belonging to A is 60 out of 100. 100 is total. Okay, so this will be 0.6 over here. Okay, probability of B, meaning a student taking CPG 607, will be 0.4 in our example, right? And over here, this is P of A comma B. Like I said, comma, think of it as and. So what is this in our example? 0.2. Okay, so now let's try to apply the Bayes theorem and see if it makes sense. Okay, so P of A given B, okay, So what we are saying is, what is the probability that a student will take CPG 591? Uh, this vertical bar basically means given, meaning we already know this fact that a student is enrolled in CPG 607. So B is given, okay? So we are saying think of it this way, we are somewhere over here. What is the probability that the student is enrolled in CPG 591? Because that is our A and this is our B, right? So as you can see, A given B, let me use a different color. So we are focusing on this part over here. B is given. So whatever is given to us, we will go focus on that region, right? And now we are saying out of this, what is the probability? It is A. So you can see this is 20 and this is 40, right? So this will be, left side will be 20 divided by 40, like half the probability, right? Okay, now according to Bayes' theorem, what is the Bayes' theorem indicating? Bayes' theorem is indicating if we reverse it, okay, let's try to calculate this. Let me indicate that by a green color. So if you focus on this, what has already occurred? A. So where are we focusing? This part. Out of which we are saying, if we already know these are the students who are in CPG 591, out of these, how many are B? Okay, B, remember, is 607. So we are saying out of these 60 students, how many are also taken B over here? 20. So this will be 20 over 60. Okay. Now let's try to put it together. What is this over here? P of A. A is 40 over 100. Oh, sorry, 60, 60, 60. A is the CPG 60, right? And this is B is. So do these match? We already know left side was 20 over 40. So if we do 20 over 60 multiplied by 60 over 100 divided by 100. So divide, I reverse, I take 100 up, right? So if I do this, 60, 60 cancels, 100, 100 cancels, sorry, not 440. Okay. So you can see left side is 20 over 40, right side is 20 over 40, so it's the same, okay? So that is, you have verified, yeah, Bayes' theorem is, really pretty commonsensical. Okay. Easy way to remember this is the way if you haven't looked at it for a while, you'll remember, okay, so if somebody gave you A given B, right? So like I said, in Bayes' theorem, what you will do is you'll reverse it first. So you will do PB given A. Okay. Then at the very end, what is it appearing? A, right? B given A. So just write it that one. So just put the whatever ended. So reverse it. Whatever comes second, put it next, right? And then left is B. So just divide by P of B. Okay. Another important derivation that we will need is how is the joint probability related to the conditional probability? See, when we say A given something, this is what we call the conditional probability. So what is the relationship between conditional probability and joint probability? A comma B, like I said, is and, right? And it's very easy to remember. So once again, if you wrote P A given B, what came second? B. So write it B next. So this will become P of A comma B, right? Okay, so let's verify it. What was P A comma B in our example? See, this was the common area over here, right? So this was 20 over 100, sorry, 20 over, it was 20, right? 20 students have taken both courses. So it was 20 over 100. Okay, let's go to A given B. What was this over here? B is given, so we are in the blue area. And out of which, so you can see this is 20 over 40, right? And what is P of B? So 40, 40 cancels. Sorry, 40, what did I do wrong? P of A given B, B is here, 20 over 40. B is 40 over 100, so this will be, yeah, so both match, right? 20 over 100, 20 over 100, yeah. So this is 20 over 100, this is 20 over 100 is the common, so both match, okay. So let's go back to, okay, so next slide is basically giving you an example. Okay, once we take a look at the Bayes theorem, which is, there's a terminology involved over here. Once we switch it, we call it the likelihood. And whatever we see, second part was A. Once we write P of A, we call it the prior knowledge. And whatever we put in the denominator, we call it the evidence. Okay. So I gave a few examples to save time. You guys can go through and see if it makes sense. When we use these terms, I'll refresh your memory. So don't worry about it. The left side is called the posterior. Okay. So for right now, just a quick, okay. So here's an important part we will be needing soon. So let me show you. Okay, P of A and B. What did we say? This would be A given B multiplied by what? The second one is B, right? So this will be P of B, right? Same way, let's pick another example. Suppose I say x1, x2. What will this be equal to? X1 given x2. Then what will I write over here? X2. Okay. So this was joint between two variables. Sometimes we will have three variables or four variables or 100 variables, right? So now let's generalize it. Okay. So this can be written as P of A given B, C. Okay. So what do we mean by over here? B and C have already occurred. Then what is the probability of A? Okay. So what will we multiply it with? See, whatever comes second, like I was saying, that's what we multiply it with. Okay. Now let's go one step further. So this is A given B, C. Okay, how can I further expand it? Can I say B given C times P of C? Okay, so you can see the joint PDF of three variable or joint distribution of three variable could be expanded like this. Okay, so in the handout, okay, so this is the expansion I showed you, A, B, C. It will come out to be this way. Okay, sometimes we will be given A, B, C, given D. Okay, and what we want to do is just separate out C given D out of over here. Okay, because we are taking the C given D out, meaning we're taking out C out of here, right? So what's remaining? AB. So then the rule is it will become AB given. See, previously it was just D, but because we took C out, that C will move over here. Okay. So once we come and need this in our derivation, I will let you know. Okay. So the second bullet, as you can see, was join PDF or join distribution of 3 variables. Okay. What if we have n variables? Then n variables becomes a product like this. Okay. And again, you can easily verify this is true. So for example, so remember this means product. Okay, so if we have P of, let's pick 3 variables, x1, x2, x3. Okay, how will we write it? Okay, we can write it as P of x3 given x1, x2, right? Times P of x1, x2. Okay, which further can be expanded as P of x2 given x1 times P of x1, right? And now I can rewrite the first part as is. Okay, so take a look. This could be represented as a product of these 3 terms over here, right? So if this could be written as x of I. So in this case, I will vary 1, 2, 3, right? P of x of I given x of 0, sorry, x of 1 to up to, or let me just make it dot, 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 x of I minus 1. Let's see if we can verify this is the case. This is the P. Okay, so for example, we are given join 3 variables, right? So I will vary. So if we plug in I equal to 1, what will happen over here? You can see this will become P of x1. And because of we are going up to I minus 1, and there's no such thing as 0, this will simply become P of x1, okay? When I becomes 2, now plug in 2 over here. What will this become? X2 given, and we go up to I minus 1. So we'll only go up to over here, right? Now plug in I equal to 3. So what will happen? X3 and given X1, X2. So this is how we can generalize. We can say P of X1, X2, Xn equal to the product I equal to 1 to n, P of xi given xi minus 1. Okay, so this is our general expression for, so anytime you run into, this summation or multiplication, pick one example, expand it out yourself, and you'll see, oh yeah, it comes out to exact, just like we discussed over here, right? X3, X1, X2 is right over here. X2 given X1 is here, X1 is over here. Sure, it turns out that way. So if we go back to the handout, this is what we did. We went 1 up to I minus 1. So that should be, so let me go 1 more minute, then I'll give you a break and we'll continue. Okay. Okay, so when we create a deep network, right, there's a probabilistic way of looking at what exactly is the network learning. Okay, as we are training it, okay, whatever training data we are providing it will have some distribution, right? Which we can represent by P of X. Okay. Similarly, as we feed in X, it produces Y. So we can think of it, the output Y is a conditional generation because this Y only came when we fed the input X. So we can, in the data world, we can view it as the network is producing P of Y given X. Okay. And the parameters it's learning, because we are feeding it many X's, it's producing many Y's. During the training process, what is it's learning? It's learning the joint distribution between the X and the Y. So this is what the network learns. And output is Y given X. So that's the probabilistic view of the learning of the network, right? Okay. And we can apply the Bayes rule to the output. So P Y given X will become what? Remember, we switch in Bayes rule, X given Y. Second came Y, so will become multiplied by Y. And X is remaining, so divide by P of X. And what's the numerator? It's the joint distribution between X and Y divided by P of X, right? Okay, so let me pause at this and give you a short break, and we'll continue from here. Okay, so before the break, we were taking a look at some of the distribution, probability distributions, joint probabilities, conditional probabilities, so that we can have a better understanding of how do we develop the theory for reinforcement learning, right? Okay, so a couple of more concepts that we need, and one is called the marginalization or the marginal distribution. So the concept of marginalization, okay, is to recover individual distributions from joint distributions. So in some scenarios, we will be given the joint PDF. Okay, so for example, we are given PDF of X1, X2, let's say. So let's say there are two random variables, X1 and X2, and we are given a joint PDF. Okay, and we are interested in finding out, given this information, given this joint, what is, for example, PDF of X1 or PDF of X2. So how do we do that, right? So it depends whether it's a discrete distribution or a continuous distribution. If it is a continuous distribution, we will integrate it over the variable that we want to eliminate. Okay, if it is a discrete distribution, so then we'll sum it over the variable which we wanted to eliminate. So for example, if we wanted to determine PDF of X1 from this joint PDF of X1, X2, which means we want to eliminate X2, right? So what we will do is we'll sum over all values of X2, and this will end up giving us the distribution for X1 only, okay? And this, once we sum over or integrate over the variable that we are eliminating, that is called marginalization. Okay. So marginalization could apply to 2 variables, 3 variables, n variables. For example, let's say you are given PDF of 4 variables, a joint PDF, x2, x3, x4. Okay. And let's say I ask you to determine from this joint PDF what is the PDF of x3 as an example, right? So which variables I have to eliminate out of over here? X1, x2, and x4. So how will we do that? We'll sum over all possible values of x1, x2, and x4. So there will be 3 summations involved over here. So PDF of x3 will be summation, 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 x PDF of x1, x2, x3, because that's given to us, right? One summation will be over, which one are we eliminating? X4, x2, and x1. So all possible values of x1, x2, and x3, right? So when we deal with RL, if it is in the discrete domain, meaning our data is taking certain integer values, not continuous values, then you'll see a lot of summations appearing, right? So for example, if I take you to our second handout, let me quickly go leave. So the lecture 2 handout, you'll see somewhere over here. Okay, as we develop the theory, do you see like 3 summations or 4 summations appearing over here? So why are they appearing? Again, because we're marginalizing, we are recovering one particular distribution out of over here. So like I said, don't be intimidated by these complex looking equations. There's a very simple meaning to it, and I'll give you a simple example to understand it better. So anyway, if it is a continuous variable, meaning the variables can take on decimal data, then suppose the joint distribution in my first example over here is represented by f of x of y, okay? And we wanted to only recover f of x out of over here. So then what will we do? We will integrate over with respect to the y variable. Then y will disappear, everything, right? What if we wanted out of the joint distribution, we wanted only the distribution of y? Then what will we do? Integrate over, if it's a continuous data, integrate with respect to x, right? Okay, if it is a discrete data, then, for example, take a look over here. This is the joint distribution of x and y. And if I sum over all possible values of y, then what will happen? I will only recover, because y will disappear now. You'll see only f of x will be, right? And like I said, this is called marginalization. So let's try to understand this marginalization from the example that we did earlier. Remember, we picked the example of 2 images, okay? And first we created the individual distributions. So this was the distribution for I1, distribution for I2. Once again, it's just a count. So don't be intimidated by all these math symbols. It's very simple. How many times 10 was appearing? It was appearing 3, so that was the individual distribution, right? From here, we created the joint PDF of I1 and I2. And what was that? If it's, for example, joint PDF 10, 10 would be if I1 is 10, exactly at the same spot as I2 10. how many times that occurs. So 10 occurs over here, so that's count of 1. Another time, where was it? At the bottom, 10 occurs in the bottom left, right? So 1010 was 2. PDF of 1010 was 2, okay? So suppose now this joint PDF is given to us. Can we recover from here PDF of I1 or PDF of I2? Okay, so like I said, what was the technique over here? So in our case, let's say we are given PDF of I1 from I2. And suppose I ask you to give me PDF of I2 from here. So what was our trick for marginalization? Sum over all possible values of I1. Okay. So let's go to PDF of I1 over I1, I2, see if we can, oops, not here. Let's see if that is the case, right? So for example, or let me see what would be easy way to see it. If you take a look, easier way, okay, easy example, and you can do both easily, but let me start out with easier first, even easier. Okay, see if I added, if you take a look in this first, right, if I2 is 10, 20, 30, 40, 50, it's easier for me to add just numbers over here rather than jumping over here, right? So first, let's try from the joint PDF, let's try to recover PDF of I1. Okay. To recover PDF of I1, what do we have to do? Add all possible values for I2. So if when PDF of I1 is 10, right? If I take a look at this up to 50, what's my sum? 3. So that means PDF of I1 at 10 should be 3. Let's verify. Is that the case? 10, what is I1? 3. Okay, let's pick another number. Suppose I wanted you to find out from this joint PDF of I1 at 30. What will be your answer? See, take a look at these were all 30, 10, 30, 20, right? Remember, we want to eliminate I2 now because we're only interested in recovering PDF of I1. So like I said, sum up all the values of I2. So 10, 20, 30. So if you added all the values when I1 is 30, what will you get? 5. So let's see for PDF of I1 at 30, what's the count? At 30, what's the count? 5. Okay. So that's the concept in marginalization. Again, piece of cake. Just add over all the values, just like I mentioned over here. Okay, doesn't matter, you're given joint distribution of 4 variables, you wanted to recover 1 or 2 out of it, eliminate all of them by summing over all possible values of the other variables, and you'll be able to recover the individual distribution, right? Okay, so coming to the handout, so now hopefully you guys have a good idea of conditional probability, joint probability, marginalization, Bayes rule, and lastly, let me see, there was one part. Okay, let me skip that part. Oh, expectation is one more thing we need. Then we'll be ready to take a look at Bellman equations. Okay, so last concept related to background for being able to develop Bellman equations is the concept of expectation. So expectation is written like this. E within square brackets or within parentheses, we put the variable. Okay, and what does that mean? That means basically average value. Okay, rather than saying a simple average, right? Suppose X has given data 2, 5, 3, 7, 6. These are the different data values we have for the variable X. Okay, a simple average would be what? 2 plus 5 plus 3 plus 7 plus 6 divided by 5, right? So what is that? 7, 10, 17, 6, 23 divided by 5, 4.6 is our answer, okay? But that's the simple average. That's not the expectation. Expectation is the statistical average or probabilistic average, okay? So what happens is, especially in the RL world, nothing is guaranteed. Okay, like when you're driving, nothing is guaranteed. Some crazy driver could behave totally unexpectedly, right? Traffic could be higher, so everybody's driving. So you're always interacting in a probabilistic environment, right? So when we talk about expectation, it is an average, but it's a statistical or probabilistic average. So to understand this better, let's pretend the probability of getting X having a 2. Let's tie it to a probability. Every number has a certain probability associated with it. Let's say 0.05. Let's say 0.1. Let's say 0.3, 0.4, 7, 8, and 0.15. Okay, because total can only be 100. So probability that X will have a value of 6 is 0.15. Okay, so now based on this information, the value is, so this is the value, and this is the probability of having that value, right? 0.05 or 0.1 in my example. So then how does it, how is the statistical or this expectation calculated? And the answer is easy. Okay, do 0.05 times 2 plus 0.1 times 5 plus 0.3 times 3 plus 0.4 times 7 plus 0.15 times 6. Whatever that number comes, that's our expectation. Okay, if I generalize it, okay, I'm given some value X, and I'm given some P of X, meaning what is the probability. So what did I do in calculating this? As you can see, I multiplied the two, right? And then what did I do? Add it. So if I add them over all values of X, that is the expectation. This is what we call expectation of X, okay? Let me give you another simple example, okay, that you can easily relate to. Let's throw a dice. A dice has 6 faces, right? Like 1, 2, whatever, 3, 4, 5, 6. 6 faces are there. If you throw a dice, okay, what is the probability of getting 4? 4 dots. 1 over 6. What is the probability of getting 5 dots? So all of those 6 have a probability of 1 over 6, right? So if I ask you, if you throw a dice, what is the expectation? This is the dice, throwing of the dice event. What is the, meaning on average, what number will you get? If you haven't seen this example, what would your guess be without calculating? 7 would not be a good guess because there are total maximum you can get is 6, right? We're saying on average, what number? What's that? No, just one die.
3.
No, expectation is a number, right? Like I showed you, as we calculate, this may come out to be 3.89. Dice has either 1 dot or 2 dot or 3 dots. If you throw on average, how many dots will you get? I want a number.
3.
Okay, some saying 3, some saying, so let's calculate it exactly according to our formula, which is this over here, right? So that formula, as you can see, how many times will I need to sum? What are possible values? 6. So if I get a 1, it will be multiplied by 1 over 6, right? P of x is 1 over 6 times 1 plus 1 over 6 times 2 plus 1 over 6 times 3, 1 over 6 times 4 plus 1 over 6 times 5 plus 1 over 6 times 6, right? So there's an easy way to calculate this. If I take 1 over 6 common, what will happen? Agreed? Okay, so now this is an arithmetic series. And if you remember from your math long time ago, if you are doing 1 plus 2 up to n, right? The formula is n times n plus 1 divided by 2. Okay, so we are adding up to 6, right? So this will be 1 over 6, 6 times 7 divided by 2. 42 divided by 2 is 21. So what is that? 3.5 is the answer. So the expectation of throwing a dice is 3.5, meaning statistically you'll get 3.5, even though there's, either you get 3 or 4. So that is the whole idea behind the expectation, right? So going back to our handout, so if you take a look at the part in bold, mu, again, don't think of it as an average. Once again, it's a statistical average, okay? For discrete data, it is x times p of x or p of x times x, okay? If you are given, for example, joint PDF, okay? Like in this example, I have a continuous probability distribution, f of x, y, based on 2 variables, x and y. So then what it will be, E of x would be, you multiply x with the joint PDF and eliminate both x and y, because in the end, we're just getting a number, okay? So that is the idea behind the joint PDF. Or in case of discrete variables, suppose you are given PDF of x1, x2, right? And you wanted, what is the expectation of x2? On average, statistically, what will be the average value of x2, right? So like I said, what will we do? We'll multiply this by x2, okay? Because we just want to get a number. So then what will we do? Sum over all values of x1, all values of x2. And whatever that calculation is, that is our expectation, right? Okay, so coming back over here, anyway, next I was just showing you the uniform distribution and Bernoulli. So you guys can read this later on. Let's come to second handout now for lecture 2 handout, which is the RL formulation. So let's start on Bellman equations and put all this background to real use. Okay. Okay, so the development of the theoretical background for RL is based on Bellman equations, as I mentioned. And Bellman equations further make an assumption. And the assumption is that all our, model that we will be creating will be Markov decision process, okay? A Markov process, right? So what is a Markov decision process or Markov process? What that means is, okay, uh, in the RL world, okay, we start with some state, okay, we take an action, we go to the second state, we take another action, so let's say A2, we'll go to third state, and so on, right? In every state, we have many actions that are possible. Let me call it A11, A12, A1N, right? If we decide to pick one action, every action has a probability associated with it, okay? For example, we may say with probability 0.2, we'll go take action A1. With probability, let's say 0.17, we'll take action A12 once we are in state S1. And what is a state? A state, for example, you know, in a self-driving car situation might be currently what is the position of our car and how is it related to what are we viewing in our camera? Where's everybody else? That's what we call a state. So as we move a little bit ahead, that's the second state. So if we decide to keep the accelerate a little bit or change lanes, that's our S2. Similarly, S3. So we keep going. Okay. Um, suppose we reach some state Sn. Okay, as we are going in our self-driving car. Okay, so in the Markov formulation, whatever action we take, what Markov says is it only depends on current state. How we got to this current state, meaning whether we came here from S3 or we came here for S9, it does not matter. Okay, only the current state matters. And from here, what do we do is the foundation of the Markov theory. So to give you an example, let's say, suppose probability of action 5 is based on S5. And previously we took, we obtain a reward, let's say R5, S4, R4, and there could be action involved over here also, S3, S2, anyway. So suppose at some point in time we wanted to calculate, you know, what is this probability of A5 given these things have already occurred, okay? So if we are doing a Markov modeling, like I said, what we did in the past does not matter. So we'll simply throw it out and we'll say this is same as P of A5 given S5 R5. Okay, the current part matters, previous does not matter. Okay, so let's go back. So we'll be dealing with Markov processes where everything based on the current state, we will decide what to do. How we got to current state does not matter. Okay, so let's go now. So a little bit of the terminology over here. In the reinforcement world, we have a concept of environment. We have a concept of an agent. We have a concept of action, state, and reward. Okay. So environment, for example, in a self-driving car, what's our environment? The camera that we have in our car, what speed sorry, not the speed. Whatever we are viewing is the environment, right? In the current environment is referred to as the state. So agent is basically our AI model. Come on, it's tough to write on this one. Okay, our agent is AI model, right? In fact, let me do this. Let me go back a little bit. Go to the previous handout. I had a better picture there. Okay, so remember, I had shown you, so this deep network over here, that's our agent in our RL mathematical formulation. An agent will take a look at the state as an input. So our deep network will take a look at whatever we are viewing in our camera, that's the state, and will take an action, either to speed up, slow down, brake, left, right, whatever, right? Okay. Um, so the output of this network, as you can see, is the action, right? And if there are many actions possible, as you know, in our deep network, what will we put at the very end? A softmax layer. And softmax turns all the outputs in a probability distribution so that we can indicate this behavior of this network as pi theta A given S. Okay. You can think of probability of an action given the state. Okay, so pi, in your own mind, think of like a probability. Theta are the parameters of the network, weights and biases. So that's what we will be training for it to take an action so that down the road, as we drive from point A to our destination, our rewards are as high as possible if it is a self-driving car. If you're playing a video game, as you started the game, as you played and played and played until you won or lost, along the way, you are going to be accumulating rewards. So you are continuously, you'll be making this network learn so that the action it takes lead to not an immediate reward. Because remember, some of you have played chess, sometimes we set a trap, we have somebody, uh, make a move so that they, take us next move win. I mean, intermediate gain, but not because of our trap, we can, be more successful. So it's not about immediate reward, it's reward over entire episode from start to finish, right? Okay, so let me now go back to the Bellman equation. Okay, so agent is our deep network. It will be taking an action. As it takes an action on the environment, we may collect a immediate reward. Okay, so that we'll denote as RT plus one. And of course, as we take an action, as we, for example, in a chess, we make a move, or in a self-driving car, we go to a different position, accelerate or slow down, right? It will change the state. That ST plus one then becomes the current state. An agent will now take a look at in this state and take another action. So this is like a loop that keeps going on until, if it's a video game, until you win or lose, or if it's a self-driving car, until you reach the destination that we had programmed. If it's a robot, whatever task we had given to the robot, until that task is completed. So we keep going into this loop and we keep collecting these rewards, right? And in the beginning, the parameters of the agent, which is the deep network, will be randomly initialized. It will continually improve, but how will it improve? So that the rewards, not just for immediate reward, but the total rewards over the entire episode are collectively, cumulatively as high as possible. So that is the goal of our. Okay, so as we develop the Bellman equations, okay, we'll indicate by this circle state S. On this state S, we will take an action. As we take the action, we also collect the reward. So this lower R is the reward. And then what do? We move to next state. Next state, sometimes we write it as S prime. So if S is the current state, S prime will be the next state like I showed you over here, right? Okay. So as you can see, the probability of going to the next state, which is st plus 1 in this example, which I call it S prime. So st plus 1 is same as S prime. Okay. So the probability of going to a next state, collecting a reward, is based on what? Current state, current action, current reward, previous state, previous action, previous reward, all the way to the beginning when we started this. Okay. So this is like a normal probabilistic system. Okay. But remember, we are going to be implementing a Markov system where we'll simplify the assumption that only this matters, the current state matters for us to go to the next state and collect a reward. Nothing in the past matters. Okay. So take a look as we apply the Markov property. This whole equation becomes the next state and the reward depends on current state and whatever the reward was, right? Okay. After last time I taught the RL course, I was thinking about just life in general, okay? And it occurred to me that life is like a Markov process, okay? For example, okay, you guys, many of you are graduate students, okay? Does it matter what did you do in your 10th grade or 11th grade or, undergraduate? Uh, uh, even previous semester, what did you do, right? You are here. What you do in this course, you'll get a reward based on what you do in this course. If you said, no, I was an A student in my undergraduate, how come I'm not getting an A? No, it has nothing to do. So based on where you are, of course, the past matters because if you worked hard in the past, collectively your knowledge is better. The probability that you will do better is higher, right? And that's what the state is. So the state is sort of like an accumulation of all your past. Okay, what you are is sum of everything you did in the past. So anyway, so what I'm trying to say is Markov formulation is not a whole lot different from real life. Okay, as we go along, present matters. How you got to that present, nobody cares. Okay. Okay, so now let's go and make it. So today I may not be able to get to all, but at least let me give you as much as I can, then we'll continue from here. So, so let's say you're playing a video game, right? You make a move, you get a reward of 50, then you played another move, you get a reward of 70, and so on, okay? In some scenarios, as you are adding the rewards, the problem is the number may start to become bigger and bigger. What if the game goes on for days or weeks? Okay, so we may run into overflow situations. So Bellman came up with the idea of a discounted future reward. So what we do is we create a discount factor. In the RL terminology, we call it a gamma variable. Hey, for example, we may say gamma equal to 0.9. Okay. So like I was saying, you made a move in a video game, you got a reward of 50. So that's your R1, right? Then next move, you got a reward of 80. So rather than your total cumulative reward being R1 plus R2, meaning 50 plus 80, when we apply the discounted future reward, this will get multiplied by gamma. So in other words, instead of adding 80, this will be 0.9 times 80 is 72. So we'll be adding 72 to it. Let's say you make the next move, you get a reward of 20. Okay. Now this is your R3. The discounted reward will now be, because it's too far into the future. So in the Bellman terminology, we will square the discount factor. So 0.9 times 0.9 will become 0.81 times 20, this will become 16.2. So instead of adding, so as you can see, the next, it will keep getting raised power, and 0.9 raised power 10 is pretty, so we are basically looking at the near future to accumulate the rewards, and the farther down in the future, the value of the reward is reduced. Of course, as we keep moving, we'll keep shifting. So because now this becomes the current state, from here we will do gamma, gamma square, gamma cube, and so on. Okay, so if we go to the Bellman formulation, the capital R basically means total reward over the whole episode. So you can see it is the next reward plus future reward multiplied by gamma. Then 2 futures away, whatever the reward is multiplied by gamma square, and so on. So we'll keep going, right? So we can define this recursively. We can say our cumulative reward is the next reward plus gamma times the future cumulative reward. So when we express one equation in terms of the variable itself, see, this is in terms of itself. So this is what we say recursive definition, okay? And as you can see, if you keep substituting, for example, GT plus 1 over here, it will come out to the exact same term. So remember, this will become RT plus 1. It's hard to write over here. Okay. Plus gamma. Now substitute this. This will become RT plus 2 plus gamma GT plus 2. So anyway, as you can see, you keep substituting the next and next, you'll come up with the exact same equation. So this is much better way to write the future rewards, right? So the goal of the Bellman is to now come up with our agent, so that as agent learns, it maximizes this G of t, which is the recursive definition. Okay, so let me go one more minute, then I'll stop. Okay, so this is our total reward, which we have defined in terms of recursively the reward being obtained from the next state. So what I'm trying to say is, if we started with a state, then we went on to the next state, to the next state, to the next state, okay? So all these rewards that we accumulated over here, those rewards are called G of t, okay? Starting from this state. Okay, so we are saying G of t is, so if we obtain a reward RT plus 1, is gamma GT plus 1. So this is our GT plus 1, meaning if we started from here and accumulated everything, uh, that is, so this gives us a nice, easy way to step by step keep moving and indicate what are our rewards, right? In the Bellmanic last comment, we will also come up with the value of a state. So V of S stands for value of a state. Okay, value of a state is basically how much cumulative reward we will get if we start from this state. Okay, and the idea is like this. Let me give you just the idea, then I'll stop. Let's say you are S1. You have many possibilities to go to S2, S3, S4, S5. So the question is, which one of these should we go to, right? And the answer is, let's remember the V of S2 tells us if we started from here and went all the way to the end, what will be our cumulative reward? V of S3 will say, if we started from here, we went all the way to the end, what will be our cumulative reward? Let's say that is 800 in this case, 850 in this case, 790 in this case, 720 in this case. So if you have to make a decision starting from S1, which one would you go to? S3 because it has 850. Now the next question is, how do we know that it is 850? Okay, we haven't even played the game yet. Okay, and the answer is, you will see it. You start out randomly, right? All of these states have random values in the beginning. V of S is random for every state. So let's say you started playing game randomly, you came to the end, and somehow you won. A lot of times you lose. So you played it hundreds of times and you won over here. Okay. Since you won over here, can you go back and put a high value to this V of, suppose this was S9? Because from here, you came over here and you won, right? So you can associate a high value. Similarly, you can work backwards and now start putting a more and more value to which path led to the victory. So anyway, we'll set it up next time and you'll see how elegant the whole setup is. Hey, so once again, please mark your attendance by going to Canvas, then quickly attendance. Today's code is 1981. And now let's take a look at our today's topics. So let me do a quick refresher on your memory last time. Hey, so I don't know if you guys have been taking a look at the recent AI news, and DeepSeek is making a pretty big disruption in the AI technology. Prior to DeepSeek, I remember ChatGPT and Llama and Gemini, they were trained using, hundreds of thousands of GPUs and millions of dollars, hundreds of millions of dollars of electricity budget. And DeepSeek, just I forgot, like $6 million is all they spent. Oh, 5 million? Okay. And they are outperforming most of the, models, especially in reasoning and mathematics, understanding. And if you take a look at, I highly recommend, take a look at their technical report. So if you just Google ArcSiv, it's for they have released, 70, 80-page technical report. And one of their models is totally trained based on RL, because the traditional NLP models are trained using cross entropy in the first phase, where they learn to predict the next token. Then they refine it using RL. And for example, the first ChatGPT was created using proximal policy optimization algorithm, which we'll cover in this course. Then later on, it's using direct preference optimization that again we'll cover in this course and see. So they came up with another version of PPO that they used to just directly train it without anything. So all I'm saying is RL is, turning out to be more important than when we started the course. So, so anyway, like I said in the last couple of lectures, to be good at anything, okay, it doesn't matter it's something academic or sports or finance or whatever field you want it to be good in, right? If you have a very strong foundation, meaning whatever are the basic concepts, if you understand them nicely, then everything becomes very easy and you can reason it, why it works, why it doesn't work, and come up with better and better algorithms or better and better techniques, and become one of the best in the field, right? So same thing with RL. Like we discussed, the foundation of RL comes from Bellman equations. We started on it, but last time towards the end, we were in a hurry, so we didn't really fully clarify it. So I'll go over it. Again, maybe even after today, some of it will make sense, some of it will not make sense. That's okay, because anytime we learn something, first time, maybe only 40, 50% makes sense. Second time you go through it, maybe 70, 80% makes sense. When you actually build something based on it, now it's getting into the 90% and so on. So don't worry, we'll be going over these concepts many, many times. So my goal is hopefully at least give you the intuitive idea, why are we doing this? What is this mathematics, and how do we make the learning of our RL system as effective as possible, right? Okay, so in some ways, it's very easy. You see, if we simplify anything, then we can see why that complex math, what's the purpose of it, right? So goal of RL, in very, very simple terms, is simply to maximize rewards. Okay, if you're playing a video game or any sports or any financial simulation you are doing, or even in the real life, your goal is to, if it's finances, make as much money as possible. You want to pick those investments or stocks or whatever property you are buying, so that of course, in anything, reward is not always positive. Sometimes, for example, if it's a self-driving car, you'll get into an accident. So the reward will be extremely negative. In the financial world, you made a bad investment, all your money or half of your money is gone. So, so when we try to accomplish this goal, keep in mind we live in a probabilistic world. Nothing is guaranteed. Whatever we are trying to do is based on high probability. If you make a decision to buy something in the financial world, you're hoping that, the in the next year or 6 months, it will grow in value as an example. Or if you're playing a sport, whatever, decisions you're making will make you win more often, right? So RL is probabilistic, okay? So probabilistically, we want to uh, maximize the rewards. That's the goal of it, right? Anytime probability is involved, keep in mind, how do we quantify it? We quantify it by the expectation. Okay, so expectation is basically the statistical average. And we talked about a very simple example of throwing a dice, right? So a dice has from 1 to 6 dots. Okay, if it is a completely fair die, so then this will be, for example, probability of getting a 1 will be 1/6. Probability of 2 dots will be also 1/6, right? So if we wanted to know what is the expectation of getting the number of dots as you throw a dice, okay, so that expectation of X, we typically write it like this. X is our event. Stands for expectation. And again, keep reminding yourself it's just a statistical average or a probabilistic average, okay? That's what expectation is. So let me write it a little cleaner. So E of X, okay? And this is simply sum over all types of possibilities that you have. X times P of X. X is the value, and P of X is the probability of getting that value. Okay, for example, if you're getting 1 dot, X will be 1. What will be the probability? 1/6. So, and sum means, this summation means sum over all. So probability of getting a 1 dot is 1/6 plus 2 dots is also, 2 times 1/6. Like I said, X is the value plus 3 times 1/6. And if we add them up, last time we saw that it came out to be 3.5, right? So once again, if somebody asks you, what is RL? Okay, it is learning a game or a decision or what we call a policy. So learning a decision, decision, which we also write it as policy as or term it as policy in the RL terminology. Okay, you can also think of it as a strategy. So for example, if you're playing chess, what's your strategy? Okay, strategy for what? Strategy to probabilistically maximize rewards. Okay, we cannot say for certain because in most of these situations, we are interacting with the environment. For example, if you're playing a game, you are interacting with what other player will do, what moves they will make. So that's what makes it probabilistic, right? So anyway, last time we talked about, we defined a term called G of T. Okay, G of T was cumulative reward. So for example, if you're playing a game, you started in the beginning and you kept, making one choice, another choice, and so on until the game ended, right? So G of T is basically the cumulative reward. Okay, let's say you made your first move, you got a reward of 10. You went to some state, then you made another move, you got a reward of 20. You got a reward of -5, and so on until the game ended, right? So this cumulative award is what we call G of T. So then we discussed is because it's probabilistic, right? We cannot simply add all of these. There's a probability associated with it, okay? So anytime probability is associated We don't just simply add. We add it like this, meaning we compute the expectation. What is, if the reward was 10, what was the probability of taking that action? Okay, if the probability was 0.2, you can see will become 0.2 times 10 plus whatever, if the probability of going to here was 0.3, 0.3 times 20. So that will be our total reward, right? Okay, so we also discussed in the previous lecture, if we are playing a game for a long time and we keep accumulating these rewards, what may happen is the number may become bigger and bigger, and it affects our learning of our system, the decision making or the strategy or the policy, whatever we want to think of it. So to make that computationally within certain bounds, we do a discounted future reward. Okay, so we do. Okay, so we come up with some factor gamma. Typically means for example, if it is 0.9. So what does that mean? So the first step that we took, the reward is 10. Once we take the next step, when we got the reward of 20, we'll multiply it by the discount factor of 0.9. So instead of saying the reward is 20, we'll say the reward is 18. Okay. Similarly, in the next step, if it was -5, it will become -5 multiplied by 0.9 square. Okay, so it keeps going gamma square, gamma cube, gamma raised power 10. So you can see if it was 0.9 and if I raise power 10, anytime the number is less than 1 and you raise it to a lot of big number, what happens to the value? Approximately will become 0. So the idea is maybe next 3, 4, 5 steps in the future will contribute to our decision making, but not 100 steps down the road. Okay, there'll be still some value. See, this might still be 0.0002 or something, but as we keep going into the future more and more, we don't worry as much. But immediately, as you can see, 0.9 or 0.9 square, which is still 80%. 0.9 square will be 0.9 times 0.9, which is 0.81. So it's 81% of the value, right? So anyway, all I'm saying is first, let's take a look at as a whole before we go into the details of the math, okay? What's the goal of RL? The goal of RL is to maximize probabilistically speaking or probabilistic rewards, right? And as we discussed, these rewards are in the future, okay? So we will also add discounted over here, right? Because they are probabilistic. What does that mean mathematically? What will we be doing over here? Computing expectation of discounted future rewards. So that is the goal of RL, right? Now we can start putting more detail into it. Okay, so again, expectation, don't be intimidated by it. It's all it means is you have some value, for example, value of a reward, 10, 20, 30, whatever it is, multiplied by probability of getting that particular value. And you sum over all of these. And like I said, as you go into the next future, you keep multiplying it by the discount factor. So now let's go and see if the math is, hopefully you will see it's not as bad. It's not as intimidating, right? Once we have the goal. So if we go to our RL CPG 591 website, and if we take a look at lecture 1 handout, Sorry, that was probability. And and before I go into it, let me just quickly 2-minute review of some of the important probability concepts that we discussed last time, right? So one of the concepts we discussed was Bayes' theorem. Okay, and it's very easy. P of A given B. Remember, this vertical bar means this thing has already occurred. Okay, if this thing has already occurred, what is the probability of A, right? And this was very easy to remember. This will be, you reverse the two, P of B given A. Whatever comes second, you multiply by that, and then you divide by whatever is remaining, which is P of B, okay? You could, the numerator over here is also written as P of A comma B. Okay, comma over here means and. So what is the probability of A having a particular value at the same time B having a certain value? If you remember last time, we took a look at to understand this joint. So P of A comma B is our joint PDF. And we took an example of two images, right? I1 and I2. Okay, so for example, let's say the value of a pixel at a certain point is 10. Okay, and if we were interested at what is PDF of, let's say 10 comma 30. Okay, we wanted to know this number, right? How would we find it? We'll go to the exact same spot. If it happens to be 30, then we'll count it as one, contributing one to the PDF. Then we'll take a look at somewhere else. Oh, it's also 10 over here. We'll go to the same spot over here. And let's say this is 20. Will that add to our PDF? No. If you remember from previous lecture example, right? Similarly, you may go over here and then if this is 10, if this happens to be 30 as well, then sure, it will add one more to our PDF calculations, right? So like I said, when we compute the PDF, in this example, I'm saying if I1 is 10 and at the same time in the exact same spot, if I2 is 30, tell me how many times that happens. Okay, and of course, we can convert it into a probability. If the total is 100, we'll divide by 100 so that sum of all those becomes. So that is the idea of the joint PDF, right? So like I said, joint PDF could be between two variables. And this could be written as A given B, P of B, which is also equal to PB given A and P of A. So either way, it's the joint PDF. So this we call the conditional probability. So PDF, a joint PDF can be converted into a conditional and vice versa. Okay, like I said, these are simple rules. If you go to the first handout on background on probability and statistics, I gave some examples of, what's the probability of getting a red card, given it is a 7, and then you can set it up like this and easily calculate it or easily verify it, right? Okay, so PDF could be between two variables. PDF could be between three variables. Okay, if this is the case, right? How will we break it into joint PDF? As we saw last time, P of A given BC. And then because I'm taking A separate out, right? Then this will be multiplied by whatever is remaining. This will be P of BC. So just like over here, A given B. So then I have to multiply it by B. So here, what was A given? What has already occurred? B and C. So then I have to multiply by the joint PDF of B and C. Now you can further go and expand it. This will be P of B given C. So what is given? C. So then I have to multiply it by P of C. So in other words, I could easily write this as P of A given BC multiplied by P of B given C and multiplied by P of C. So this is same as the joint PDF, okay? Sometimes as we learn the setup of the Bellman equations for RL, we'll run into a need for one more rule, and that rule goes like this: P of A, B, C given D. Okay, so what we may want to do is we may want to take a certain term out of this. So we may want to say, what if I take this, separate this part out from this joint conditional. So D is given, but I'm interested in the joint behavior of A, B, and C. Okay. So since I took the D out, this will become P of, sorry, since I took these, see, normally if you take a look over here, AB was dependent on D. But also at the same time, we needed to know what is the value of C, right? But because C has gone, so now we will say, oh, for that, given that value of C, and AB always depend on D. So this is how we can separate out one variable, one of the joint PDF variables, and express it in the others, right? So these simple rules now we will use to learn about the Bellman equations. So let's go to, and let me give you another idea of Bellman equations also. Okay, so that we get to see the intuition behind it. Like I said, the math is a little bit intimidating. You see, if I show you all the equations like you saw last time, right? Okay, so you'll see, wow, there's, these four summations going on and conditionals going on and this and that. But with our background and the intuition we have developed, you'll say, oh, it's not that bad. Okay. So anyway, and the final result is beautiful. Okay, so it's not like you have to memorize how do we came up with that. If we can understand how we came up with that, then we understand if we can understand the final result, then we'll have a better intuition how it works. How can we make it more efficient and perhaps even improve it, right? So anyway, so let's go. Okay, so let's go from the beginning and very quickly go over it and see if it makes sense. Okay. So one of the first things we will do is keep reminding ourselves what's the goal of RL. Goal is to maximize rewards probabilistically. Whenever we say that, what does that mean? We'll be if R is a reward. See, think of T as T equal to 1, T equal to 2, meaning as we are playing a game, we are moving from one time step to another. Okay, every time we move, we get a reward, R1, R2, and so on. Okay, so, and what does expectation mean? In simple terms, average, statistical average. Okay, so if there was a certain probability involved in it, okay, so let me emphasize this again. Let's say we had state one. We got a reward of 10. And let's say the probability of taking that particular path was 20%. Okay. Now we go to state two. Probability of something was 0.3. We got a reward of 5. Okay, then we went to state 3. And as we made a decision, we got a probability was 0.1, and we got a reward of, let's say, 20. Okay, so if this was the scenario, if we don't worry about the discounted reward, my question is, what is the expectation of these rewards? Okay, so again, think of it as an average, right? So if I did not have the expectation, what would be the average reward? 10 plus 5 plus 20 divided by 3. I went 3 steps, right? So that's my average reward. But like I said, in a probabilistic world, each one of these has a certain probability associated with it, right? And what is the formula for expectation? X times P of X and sum over all things, right? So what will the expectation come out? It will be 0.2 times 10 plus 0.3 times 5 plus 0.1 times 20, which is basically 2 plus 1.5 plus 2, so whatever, 5.5 is my expect. So on average, I'm getting 5.5 reward if I follow this path. Okay. So anyway, that is the idea behind an expectation. So coming back to the goal of RL, what's the goal of RL? Maximize, because we want to come up with a model which gives us the most reward, right? Probabilistically speaking, meaning on average, it gives us the best reward. Okay, so before we take a look at, okay,
I have a question. Yeah.
Sure.
So my question is, so the award, we set the award. We're gonna say if for example, a Tesla car gonna go through this green light, we're gonna give it 10. If it doesn't, we're gonna give it minus 50. But for the probability of taking this action, how is it set?
Where does the probability come from?
Yeah.
Okay, so yeah, let me explain that. Okay, so remember last time I showed you a diagram where we'll be creating this model, right? This model will take a state as an input. Okay, and okay, let's pick an example. Okay, let's say you're playing tennis. Okay, I assume you guys know a little bit about tennis. Okay, here's player 1. Here's player 2, right? And let's say the player 1 hits the ball straight to the player 2. Sorry, player 2 hits the ball to player 1, right? So now the player 1 has, let's pretend, 3 choices. Okay, player 1 can, let me use a different color. Player 1 can send it back, right? Meaning reply back to the center, or reply back to the right, or reply back in this corner, let me call it left. Okay, so if if we were creating a model, let's say this is a robot which will compete against another human, let's pretend, right? So in that case, this model will have 3 outputs. Okay, center, left, and right. Okay, if we put a softmax function over here at the end of our model, remember softmax will produce some of the probabilities to be equal to 1, right? So let's pretend in the beginning, this model is totally random. So my question is, given a state, the state is player 2 is standing over here. We received the ball in the middle of the court, and now we have to make a decision, send it back to the center, right or left, right? So we know the state. we have to decide on this action. Okay, so in the beginning, if this is totally randomly initialized model, my question is, what will be the probability of C, probability of L, probability of R? Okay, 1/3, 1/3, 1/3, right? Because it's randomly picking what? Okay, now if you're a tennis player, you will recognize, okay, let's pretend P2 is right-handed, okay? If you put the ball in the corner, and that's called the backhand of the player, most players are weaker on the backhand side. Most likely, eventually, this will lead you to win the point. So this, if it is a good model, what I'm trying to say is most of the time it should pick this left action over here as it learns and learns and learns. Of course, if it is a left-handed player and we are training it against it, it will be the reverse. It will start to put more and more balls on the right side, right? So what I'm, just to give you an initial idea, if this is a right-handed player, as our model interacts with the other player, it will gradually start to increase this so that, because you don't want to make it 100%, then the second player will always stand over here and not even take it on the backhand. So, right? So maybe as this model gets better, depending on the capabilities of the second player, this should be, let's say, 0.6. This should be 0.1s. And this should be 0.3 as an example. Okay, so this is where the probabilities come into play. So goal of RL is, like I said, and with each one of these, there will be a reward associated. For example, gradually, this will turn into a reward of, let's say rewards vary from 0 to 100. This may turn out to be reward of 70. This may turn out to be reward of 10. This may turn reward to be 20. So gradually, the model will learn where you are getting the rewards as it keeps interacting. So that is the idea behind RL, right? Okay, so once again, we want to uh, get the maximize the expectation of the reward. Okay, so let's see if everybody understand equation 3. Okay, what is GT? As I mentioned, GT we had defined last time. This is the total cumulative discounted reward. Okay, um, so see, this was GT, the reward in the next state, plus gamma times GT plus 1, okay, which is the cumulative reward in the next state, right? So we defined it recursively. And one of the reasons is, as you will see, if we can come up with a recursive definition of learning the policy. By learning the policy means, remember in the beginning, these weights are all randomly initialized. Every action it is producing is equal. Okay, we wanted to learn to gradually pick those actions with a certain probability so that our total rewards are, the expectation of the total rewards is as high as possible. So anyway, going back over here, GT is the recursive definition of the cumulative future reward discounted by gamma. So what's our goal? Our goal is to maximize GT in a probabilistic manner. When we talk about maximizing this, what does that mean? We'll be maximizing the expectation. So let's see if this equation 3 makes sense. So what does it mean? Expectation of GT, which is the average cumulative future reward, and vertical bar means given, and given the state. So in other words, if I so let's say this is our starting state, right? Remember, with certain probability, we'll go to some other state, certain probability will go to some other state. And we keep going, and finally we win the game or lose the game, okay? So as we are moving in this trajectory, every time we make a decision, right? How do we make a decision of our model? Let's pretend has three outputs. Again, giving you the tennis example, hit straight back to the right corner, to the left corner, right? Okay, so there will be a certain probability in the beginning. They will be all 0.3, 0.3, then they will start to change 0.1, 0.2, 0.7, and so on, right? So this is our discounted future reward, which we are saying will be called GT. Okay. And so the expectation of this pi means policy. Policy, think of a policy means our model. As we adjust the weights, it will change the probabilities over here. So pi is referring to our decision model over here. Okay, what it has learned, okay, because that is what will produce the probabilities over here, right? And this is what we are trying to maximize. So if we go back to our handout, okay, so this expectation given a state, GT is the total cumulative reward till the end, till we win or lose. E is the expectation. Pi means following parameters of the model, whatever weights and biases it has, because that will decide probabilistically how are we moving, right? Okay, so then if we term that as V pi of S, okay, so going back over here, okay, so first thing in Bellman's equations, what we are trying to do is come up with a measure which we call V pi. For example, for starting state, this is V pi of S1. Then as we go over here, let's say I call this S2, I call this S3, I call this S4. Okay, so then this will be V pi of S2, this will be V pi of S3, and so on, and V pi of S4. Okay, so the question is, what exactly do we mean by if we have some state, let's say S of X, and what do we mean by V pi of S of X? Okay, so in plain English, think this is called the value of the state. Okay, so what value are we referring to? We are referring to the rewards that we will get from this state till the end. So again, anytime we talk about rewards, it automatically implies we're talking about cumulative rewards. Okay, so if I again try to show, let's say this is some state S of X, this is some V pi of S of X. So we started from here, we went to many, many states. Okay, eventually we came over here. Okay, so let's pretend somehow this is our current state. Okay, so I'm trying to clarify there will be a number associated with the state, which we call the value of a state. Okay, if that number is, let's say, 20,050, let's pretend. All right. So if this is the V pi of S, what does this number means? Okay, what it means is if we start from here, keep making decisions. As we make any decision, what will be our deciding factor? Like, how will we know if there are three choices, which choice to go to? Okay, keep relating it to, remember, we have a model. The decision-making or the parameters of the model are represented by pi. Okay, meaning based on that, it will give us a probability of what actions to take. So if you had three choices to go forward, how will we decide if we wanted to go one particular action? Whichever probability is higher, right? So let's say L has a probability of 0.4, and the others are 0.3 and 0.3. And this is then we will go to this state, right? We'll accumulate some rewards, then we'll accumulate some more rewards probabilistically till we end. Okay, so in this whole path till the end, starting from here, if we accumulate all those rewards in a probabilistic manner, that is the value of the state. Okay, so let's pretend from S of X, the next state, one of them has a V pi of S of 19,000, another one has 18,000, another one has 21,000. Or let me make it easy, 2,000. So one has 19,000, 18,000, 20,000. Okay. If somehow we knew the V pi over here of whatever that state is, like I said, that's the number 19,000, that's the number 18,000, that's the number 20,000. Okay, you can think of it this way. One way we can simplify our decision making is we'll simply say, hey, go to the state which will eventually give us as high total rewards as possible. So in this case, the natural decision would be to go to the state. So to go to the state where we know we'll get, if we keep moving from this state onwards, we'll get 20,000 reward. So the value of state is giving you an idea. Oh, we have a chance of getting this reward if we pick that. So once again, it's like, hey, as we keep going, one way to make our decision, see, we want to decide, oh, we have three actions we could take. Which one should we take? Okay, what I'm trying to say is, until we go to the end, we don't know what that cumulative reward is, right? We haven't even finished the game yet, but somehow, and we'll answer that somehow in a second, if we knew, oh, reward here was 50,000. If we go back over, reward over here was, let's say, 10. As we go backwards over here, this was 50. So V pi of S over here will be 50 plus 10, 60 as an example. And we keep going backwards, right? Okay, so once again, value tells us the quality of the state, how good that state is, so that we can take a look at our next future states and make a decision. Oh, this one has a higher quality. Okay, and how do we know the quality? Because like I said, that is the sum of discounted future probabilistic rewards. Next question, how do we know what those are? We haven't finished it yet, right? This is where the Bellman is going in that direction so that we can compute that. Okay, So I'll answer that. How do we know what all these rewards that we will accumulate in the future, how do we find them? So let me leave that as an open question right now. But for right now, let's say if you had three choices, you were given the value of each one of these states. Okay, let's say 200, 300, 400. Okay. So then where would you go next? To the 400. Because there you will, if you started from here, there's a bigger chance you'll accumulate more reward. Okay. So anyway, let's come back
Excuse me,
over here.
just a quick question. For me, it will make more sense to go with a smaller value because at the end we will have a small one, like the result value state. It will be a small one, and if we are following the bigger one, we will, I feel like, go away from it. No.
No, because see, to give you an example. Okay. Okay, so let's say this reward we get as we take an action, right? So the reward was 50 over here. Okay, the reward was 70 over here. So if I don't worry about the discounted reward, then you can see the value of this state is 50. The value of this state is 120. Okay. Similarly, as you keep going, you can see this number is getting bigger and bigger. So value of this state, for example, let's pretend is 30. Value of this state, let's pretend is 20. Okay. Okay. So let me see if I can suppose over here, if uh, 30, 50, yeah, okay. So let's make it, for example, I wanted to show you I wanted to show you three choices. Okay, let's say you are going over here. You are going over here. Let's pretend, right? Okay. So this 120 is the reward over here. Let's pretend for this state, it is 80. Okay. So if you're coming from here, right, as you can see, yeah, this was 80, sorry. And this is 120 over here. Okay. So from here, like I said, if you're going to a state with cumulative reward of 80 or a cumulative reward of 120, because your goal is to accumulate more and more rewards. So the higher value is what you want to choose, not the lower value. I don't know if that made it clear or not.
Yes, so the goal is to get more rewards rather than choosing the shortest path, if I'm getting it right.
Yeah, see, in this case, there is no short path or long path. It is whichever path we take where as we keep accumulating as we keep summing the rewards, we want that sum to be as high as possible.
Okay.
Okay, so anyway, as you can see, because the GT is that sum, right? It is the total rewards, and we expressed it in a recursive way so that it's the future reward plus gamma times the GT of the next state, okay? But if you take a look at the GT, the meaning of the GT is, once again, from that state. So if you are somewhere over here, doesn't matter how we got here, we keep going, keep going, keep going over here. This is our total GT till the end. So GT is the total cumulative reward, starting from a particular state. Okay. And to make the calculation easy, what we are saying is, if we got an RT plus 1 over here, starting from this state, this reward is RT plus 1. And let's say from here to here, this is GT plus 1, okay, the accumulation. Then what we are saying is this GT will be RT plus 1 plus GT plus 1, okay, meaning reward to go to the next state, and the cumulative reward from that state to the end. So this way, when we define something in terms of itself, GT is defined in terms of itself, we refer to this as a recursive definition. And that will help us, like I said, set up the learning eventually, as you will see in a few minutes. So anyway, so starting from a state, GT is the total reward, right? And because the actions are probabilistic, we'll try to take a look at the expectation, and that expectation is our value of that state, okay? So if you take a look at equation 3, what is the value of a state? It is the essentially total reward starting from that state. So once again, at a plain English level, if I am at a state, what is the value of that state? Suppose this is some state S. What is that? From here, doesn't matter how I probabilistically move. The probabilistic GT is the value of the state, the total reward starting from that state. Okay, so that is the definition of the value of a state, expected value of the GT starting from a state, right? And now, if, remember, GT itself was defined recursively as the next reward plus gamma times all the future rewards starting from state T plus 1. Okay, so then if we substitute this GT by the definition of GT, recursive definition of GT, this becomes RT plus 1 plus gamma GT plus 1. So you can see so far up to equation 3, it makes perfect sense, right? Now let's go and by definition of E, right? For a single variable, okay, if I have a single random variable, as we discussed, what's expectation of X? Sum of X times P of X, right? What if this is not a single variable? This is many, many variables, right? Meaning just like in 2 images problem, we had a PDF of I1, A2, I2. So in this particular case, we have S prime means what are the possible next states, or what are the rewards that we will get in any of the next states, GT plus 1. If there were 3 next states as an example, so see if let me see if this is S, right? Suppose there are 3 So whatever those are, we are referring to as S prime. S prime in our definition is the immediate next state, right? RT plus 1 is our reward that we will get as we go to the next state. Okay. And of course, these states are different. But I'm writing it as S prime because in our math, we will do sum over all these three possibilities, right? Okay. From each one of these next states, you can see if we went all the way to the end, there will be cumulative discounted reward, which is GT plus 1. So pictorially, you can think of it this way. Even though I'm writing all of them as GT plus 1, they are different numbers with different probabilities. Okay, so again, what we will do is we'll sum over all the GT. So going back over here, all the GT plus 1s. Okay. So what I'm trying to say is in this particular case, this expectation that we are trying to compute in equation 4, our goal is to compute this expectation, right? So think of it as if this was, let me see if I can write it like this. Maybe this will make more sense. Think of this as X in our example. If I was saying compute E of X, what will that be? It will be sum over X multiplied by P of X. So what I'm trying to say is this X over here, as you can see, is we wrote it exactly like this. That's our X. Okay. But P of X is not a simple probability. It is a joint PDF now. Why? Because we have rewards, we have states, we have cumulative future rewards, we have actions. So this is this P over here, this P of X is actually a joint PDF of 4 things. What is S prime? Next state. R, the reward that we will get as we go to the next state, GT plus 1. From that next state, what are the cumulative rewards? Okay, A is the action, whether we are, in case my tennis example, we are hitting back in the center, left or right. Okay, so as we expand this, because these are 4 different variables, 4 meaning a joint PDF of 4, now you can see how many summations will there be. See, for a single variable, it's just one sum. Okay. If it's a PDF of 2 variables. So in other words, what I'm trying to say is, okay, so let's say you have 2 random variables. Okay. If you wanted to find out what is expectation of E of X1, how will you write it? You will write it as summation X1 P of, now it's a joint PDF. Okay. And there will be 2 summations for all values of X1, all values of X2. And we are interested in what is the average value of X1. So X1 stays X1, but 2 summations will be involved. So if there were 4 joint PDFs, there will be 4 summations involved. Okay, so anyway, this step hopefully will now make sense. All we are doing is applying the formula for the expectation, right? Let's see if the next step makes sense. Okay, if you take a look at the next step, what did we do? Okay, if you take a look over here, how many joint PDFs were there? 4, right? S prime, R, GT plus 1, and A, right? So what did I do over here? I removed one of them. Okay, and that is over here. So I removed A given S. Remember we talked about what happens if you remove one of the variables. So if we talked about it, P, A, B, C given D. If I take out P, C given D, what happens to the rest? Given CD, right? So that is exactly what we did in the next step. I took out A, given S. So what does that mean? Previously, the four variables were dependent on the state we are in. Now, what are they dependent on? Action and the state. Okay, rest we left it as is. Okay, so all I'm saying is step by step, all we are doing is applying one rule of join PDF. So to simplify it as much as we can so that we can come to a final answer, which is very clean. Okay. So if you keep going, I have a good explanation of it. See if you can, each one of these steps, you can see, and this, I'll give you this as an assignment. What you will do is give me the explanation of which rule did we apply to go to the next step, to go to the next step. And this will help you as well understand all of these, right? So anyway, one at a time, like I said, I'm going from one step to another step to another step. Okay, for example, let's pick one example over here. Let's see if we are over here. Let's see from here, what are we doing over here? Okay. So if you take a look over here, this P GT plus 1 S prime was being multiplied by R plus gamma GT plus 1, right? Okay, so if we multiply it by this part over here, okay, so then as you can see, gamma we can take out because that's not dependent on the cumulative reward. So gamma could be moved out of this summation, Okay, and then you will see this is same PGT plus 1 S prime, and we multiplied it by this part over here, right? Okay, and if you take a look at R, okay, R is not, so R could be taken out of this summation because R is independent of the GT plus 1. Okay, R is the reward that we get to the next state. Whereas GT plus 1 is if we started from the next state and went all the way to the end. So this R could be moved out of this summation. And that's why you'll see this R got moved over here. Okay, so this part is 100% same as this part. Okay, and the rest of it, I left it as is. Okay, so, you know, it might take you a little bit of thinking, but one, you know, simple application of these, in other words, what I'm trying to say is, let's say you had something 2 times x squared sum over all values of x equal to, let's say, 1 to 10, right? So what I'm trying to say is this 2 has nothing to do with this x, so you could move it like this. You'll get the same answer. Okay, so some of these simple tricks we are doing, if the variable inside the summation is not dependent upon on which part are we summing, we can take it out. And okay, so anyway, coming back to, okay, so if you keep going through, hopefully you'll be able to justify it. if there's any confusion, you'll, as you go through it and say, oh, I don't understand. How did we go from this step to this step? Don't worry, I'll stop by and I'll explain it to you. Okay. The final answer, as we keep simplifying this, is right over here. And this is the Bellman's equation. So let's see if we can understand it at a high level. Okay, so at a high level, what is it saying? Okay, we are trying to come up with a formula, with a calculation so that we can, let's focus on the left-hand side. What are we trying to calculate over here? Value of the state. And what does that mean? Yeah, so if we went somewhere, right, as we were playing a game or something, let's say somehow we are here, and this is some state S. Okay, the value of the state is if we started from the state and when completed the game, okay, what is the expected GT given that state, given meaning starting from the state, GT is the cumulative reward, which is discounted. That is what we mean by the value of the state, right? So what Bellman is trying to say is, okay, think of it this way. From here, let's say there were 1,000 states involved. Okay, from here, there are 3 possibilities. From each one of those, there are 3 possibilities. If you have to go 1,000 of these, just imagine how many calculations we will need to do. Okay, so Bellman's goal is, so let me give you his goal. Then you'll be able to see it very easily. Goal is to simplify this thousands of future step calculations so that we can come up with this value. Okay, so he came up with a very beautiful idea, and the idea is like this, or let me say Bellman's idea. If we can define V pi of S in terms of V pi of S plus 1 or S prime, S prime is the next state, then it becomes, that calculation becomes extremely easy, okay? So in other words, let's say 3 possibilities. Okay, this V of S, if somehow, so let me call this S1, S2, S3. Okay, let's say with each one of these, there will be a reward, right? Okay, so let's say the reward is probability is 0.2. And let's say reward is 20. If starting from S, we go to S1. Okay, let's go to the second state. If the probability is, let's say, 0.3, reward is, let's say, 30, probability is 0.5, reward is 40. Okay, so what will be then V of S, in terms of V of S1, S2, S3. Okay, so let's see if we can do this for this simple example. If we can do this, Bellman equation will make perfect sense. For this simple example, what would you say? V of S will be, let's write it out. What's the probability of going to S1? 0.2. So will be 0.2 times, what's the reward? 20. You guys agree? Okay. What's the probability of going to S2? 0.3 times 30. Probability of going to 0.5 times 40, right? So can we write it like this? Because we are adding it 3 times, right? Anytime addition is involved, we can, how many actions were involved? 3, right? So could I write it probability of taking this action given the state times R? Okay. But now there are 3 states involved, right? If somehow I know the value of each one of those states, then this value of the state, again, there are 3 future states, right? So I'll be summing those up. So as I'm summing those up, right? How do we, in our terminology, we indicate the next state? What symbol do we use? S prime, right? So now let me take you to the equation and see if it is starting to make a little more sense. Okay. Probability of A given S over all actions, right? So in our example, what was that? As we said, 0.2 times 20, 0.3 times 30. Did we also come up with the same thing? First part is clear, right? Now let's go to the second part. Okay, as I mentioned, there are 3 states, right? In S1, S2, S3 in our example, but in general, what do we call them? S prime. And now, once we are in S prime, what is given to us? What has already happened? We have already taken an action on a state, right? And now, because there are 3 future states, what will you see over here? Sum over all the future state, all over S prime possibilities, which is S1, S2, S3, right? As we go from this future state, as we go to this future state, what are we getting? Reward, like in our example, 20, 30, 50, right? And this reward, because remember, this is the cumulative, the value of a state is cumulative all the way to the end. Okay. But we don't want to go all the way to the end. We want to come up with a simple formula so that we can represent calculation of V pi of S in terms of S prime, V pi of S prime, right? So you can see if we can represent it as gamma times V pi of S prime, then we have a beautiful recursive relationship. Okay. So hopefully you can see, there's nothing magical about it. It's like simply going back to my example, try to relate it to this simple scenario over here. Okay. All these S1, S2, S3 are our S prime. Okay. We can write it in terms of the value of S in terms of V of S1, which in general is V of S prime, and V of S2. And what is V of S1? We'll go from here all the way to the end. Okay, so at least, okay, we haven't, again, fully answered it yet. So far, what is Bellman telling us? The value of a state can be calculated by summing all the probabilities of the actions multiplied by the reward that we will get plus the value of the future, next value of the next state. And all of this will be weighted by the probability of going to that state. Okay.
Just ask you a question going back to the other page with you. The three choices that you have, S1, S2, S3. The reward value is associated with the probability. So those are your three choices, you know, say they're back to your tennis equation, left, right, and center.
Mhm.
Decimal is the probability of
Taking that
choices.
taking that choice. Reward comes, okay, good question. In case, in your question will lead to the completion of this Bellman equation. So it's a good question. So let me answer that indirectly right now. And if it's still not clear, ask me again in one more minute. Okay, so let's go to the Bellman equation, right? Okay, so remember, okay, first let me give you a hypothetical scenario. How many states will we have in a certain scenario, like a chess game or tennis game or, you know, any other RL problem? We'll have millions or billions of states, right? Okay, so what Bellman is saying is, if we know the value of each one of those states, let's say S prime and so on, all the way to the end. So millions of states, billions of states over here. If we know that somehow we knew the value of each one of those states. And again, what does value mean? From here onwards, what kind of rewards we'll be getting in a cumulative probabilistic way, right? Okay, so let's say you are here. This is your current state. You have three possibilities. If you know the value of this one, let's say the value is 2000, value is 18,000, or 1800, sorry, value is 1500. Okay, somehow you knew those, right? Then which path will you take from here? Whichever will end to, because remember that number indicates very good reward moving forward from that state.
Can I give the example because as we discussed the chase game. So regarding the chase game, so if you can just calculate the position weight, so whatever the stage, whatever the you have, you can calculate the steps. So if you want to make one move, then after the move, you can recalculate all the steps. So there is three possible moves. So for each possible moves, calculate the each based on the weight total values yours. So if you move this way, it will give a one step and there will be certain values. If you move to another option, it will give certain values. If you another option, it will give third value. Means all are yours. So you will find that which will be less yours.
Yeah, so let me further clarify that. So one possibility is, right, we suppose millions of states are involved. Because our goal is to create a model, like a deep learning model. And in our tennis example, it will have three outputs, but in chess example, if there are 64 or how many, I mean, you may have hundreds of those moves, right? So rather than calculating before our model is ready, trying to go and calculate the billions of these values, that's one possibility, right? Because once you know the value of each state, then as soon as you come to a state, your decision is easy. You take a look at which path will lead to a future reward, right? So, but is that feasible? Creating the values of billions or trillions of states. Okay, And the answer is no. It will take us forever. The RL will never be ready. Okay. So that's where the beauty of Bellman's equations comes into play. And he says, you don't need to calculate all those billions and trillions of values if there are that many states. Calculate the value based on just your immediate next states. Okay. So as you start out, okay, do you know the value of what the next state is? No, it may be random. Okay. Completely random. So what you do is you randomly start playing the game in the beginning because you are trying to make this model learn what are the best policy, meaning adjusted weights so that in each state it picks the best action, right? Okay, so what you will do is you'll start out completely playing randomly. Once in a while, you will win at the very end. Okay, because in some games, in some video games, as soon as, like you have a star shooting game, as soon as you hit, you get a reward. In some games, like chess, you don't get a reward, or you may get a reward as you, remove a piece of the opponent, but your big reward comes in at the very end. Okay, so think of it this way. Do we know if these values were given to us? Can we calculate this value in terms of these values? If V of S prime was given to us, can we go backwards and calculate it? That's what the Bellman equation is. See, let me take you back over. And that's the example I was trying to show you over here. Oops. So in other words, if I gave you V of S1, V of S2, V of S3, from those, can we apply it in this equation and find V of S? Yes. Let me put Bellman's equations back again. Okay, if all three future states, their values are somehow given to you. Okay, do we know gamma? Sure, gamma is a fixed number like 0.9. Okay, do we know the rewards as we went from here to the three states? Sure, because we already are saying in a tennis game, or again, assuming these values are given to us, we know what reward we will get, right? Okay, so everything over here is known. We can easily calculate V pi of S if these values are given to us. This V pi of S can be calculated. Okay, so final clarification to the Bellman equation, we keep playing the game randomly. We somehow win. Okay, can we go now backwards? And calculate this value based on that if we took this action, we won. Okay, so going backwards, we'll start filling out the values. Okay, does that mean we will know each and every value if there were trillions of state involved? No. But we will, if we can now, so this is where the deep learning comes into play. So let me sidetrack over here and ask you a totally unrelated question, okay? Suppose you were training a deep network to recognize dogs, cats, birds. A simple 3-class recognition, okay? You presented some training data. If it is a dog, it learns in the beginning, of course, it will make a mistake. You will have a loss function over here. You will go back, adjust the weights, so that next time it sees a dog, it starts to recognize it. And let's pretend we had pictures of 10,000 dogs, pictures of 10,000 cats, picture of 10,000 birds in our training data set. We train the network. Network is ready. Okay, my question to you is, so 2 minutes.
Okay.
Or 5 minutes. 5 minutes. Yeah, you can. Okay, so coming back to, because today, if we can get a really good intuition of Bellman, then we'll be all set. So today we'll have a short lecture. I wanna at least get to the complete understanding of the Bellman. So my question to you is, we trained a network with 10,000 dogs, 10,000 cats, 10,000 birds. Suppose network is ready. Okay, if I give it a different new picture of a dog, okay, what's the probability it will recognize it as a dog? Low or high? High, because it's already learned, right? That does not mean, suppose there are millions of pictures of dogs. Most of them I will recognize as a dog if we did a good job in the training. So what I'm trying to say is, even though there are billions or trillions of states over here, we don't have to worry about calculating the value of each one of those states. As long as we create our network based on the Bellman equation, okay, which means it learns to go backwards because it already know, oh, that one started as a really, that we won somehow coming to this path over here. So now if we can go back to backtrack and keep filling those states over here, values of the states over here, then it doesn't matter even if it is a different state, it is starting to learn how to move forward to eventually win. So, so that is the idea, beautiful idea about the Bellman equation. Okay, so in our model that we create, it's hard to write over here. Okay, in the model that we create, okay, our input will be a state. Output will be, okay, there are a couple of possibilities over here. It could be if there were 3 actions that were possible. One possibility is put those 3 actions on the input. It will produce the value for each one of those next states. So in the next few lectures, we will further go into how do we set up the model. And as you will see, there will be different ways to set it up. Set it up as value learning, Q learning, but being able to calculate the value in terms of the future value of the states is the key of the Bellman. Even though the derivation is intimidating, the final answer is, again, very, very commonsensical. I highly recommend, if this was a little bit confusing, go to this example that I gave you. Just a simple starting from one state with these 3. Assume some V of S1, assume it's 200, assume this is 300, assume this V of S3 is 400. Okay, plug it into the Bellman's equation and see if you can compute backwards, given V of S1, V of S2, V of S3, can you compute V of S given that on this simple example? If you can do this, I guarantee you, as you take a look at this Bellman's equation, this will start to make perfect sense. Just expand this equation. S prime will be three. One of the three, S1, S2, S3 actions will be one of the three actions. V pi of S1, S2, S3 is given to you. Gamma, you'll fix R, just like I gave you in the equation. Yes. It's going forward. Very good point. The equation says it's going forward. When it learns backwards. Because like I said, in the beginning, it's random. You don't even know. Pretend you're a basketball player or a tennis player. You're hitting left and right. You don't know what's a good style. Where do I hit? What strategy or policy should I pick, right? So like I was saying, the whole idea is you randomly start playing. And somehow, luckily, you end up winning. And then you think about it, oh, that was, and from that point, you go one step backward, and keep adjusting yourself. To give you an example, go to the gym and start shooting basketballs. Okay, even though you don't have no idea about basketball. Then you start saying, oh, if I put my hand a little bit up and follow it through, it gives me better rewards. So that's the policy you are learning after seeing that you actually made the basket. Yes. Yeah. It will be used to train our network, which is learning the policy. Okay.
I have some basic questions.
Sure.
The rewards that we are getting, are they defaultly given to the state, or how are we getting the rewards?
Okay, like I said, in some cases, the reward doesn't show up till you actually win. Okay, so then remember we are using discounted rewards. So even though there was no reward as you went from, like in a chess game, if you make a move, nothing happened. You didn't. So the reward is zero immediate reward. But if you take a look at the discounted reward, when you go backwards, it will have a value. So one of the assignments we will do is we'll set up the rewards. In some cases, the rewards are well defined, meaning you know immediately if I took this action, what will be the reward? Yeah. Yes. And like I said, two cases, in some cases, the rewards do not occur till the very end, which is okay. We'll randomly go to the end, collect a reward, and go backwards and adjust the discounted values.
And the discounted reward is basically final reward, right?
Yeah.
Then in the formula, it shows for every state, right?
Yes.
State reward, R plus gamma, next state reward, R square, gamma square plus.
Yeah. So like I said, depending on type of game, right? Like in chess, for example, if you kill one of the pieces of the opponent, you do get a reward. In some games, only reward at the end. So if there is an intermediate reward, that R plus will get added. But if it is not, it will be 0 plus the discounted reward, but still there's a reward associated with that state. As we program these, a lot of these questions will become crystal clear as you see how are we applying this equation, how is it learning, okay? I also highly recommend take a look at the DeepSeek's approach to RL. How did they made it so smart? It is RL and it's a beautiful concept. It's like we keep experimenting and keep analyzing. It's like maybe, Scott, as you play a music, you are trying different tunes and perhaps one of the tunes you say, oh, this is great. So then you go back and start to compose the whole thing based on what you discovered. So it's like trial and error in the beginning, and whichever trial turns out better, you go back and adjust your strategy or policy so that more and more you are probabilistically achieving that.
Dr. Lagoon, I was thinking that, so when you're moving forward, say for the first, I don't know, times or whatever you need, the rewards are random until you win. And then you send those numbers back.
States are random, but rewards are there. See, if you lost the game right away, you made a bad move, the reward would be negative 10,000 as an example. You got into an accident. So rewards are based on what you are doing, but you don't know what action to take, so the actions are random. As you do trial and error, eventually some of those trials and error will end up being positive. Any positive experience, you go back to make yourself better. So that is the whole goal in RL. Okay. Sure.
In relevant situation, the value of state is taken based on the policy, right?
Yes.
It means they already, the momentum is already moving in a policy.
Correct. Probabilistically. Yeah.
So we were explaining, like, the next state, having the value 2000, having the value of state 2,800, you just take, but it will choose 2,000. Right?
After it has learned.
But the policy is not changing, right? Because all.
Yeah, that is assume the network is trained, policy is fixed. Yeah. After it has learned. Yeah. But in the learning process, the values keep changing. All right, so there's a meeting over here. So today we'll stop our class at this time. All right, so last time we were looking at understanding the Bellman equations. As we talked about, the key to reinforcement learning is understanding Bellman equations. And even though in the beginning they look a little bit intimidating, but as we have talked about towards the end yesterday, it's really, see, in my opinion, nothing in the world is complex. Okay, everything has a very commonsensical, no matter how complicated of a math you see, there's a very commonsensical motivation or explanation behind it, right? Same for Bellman equation. So if you recall, once we went through the, for example, the Bellman equation handout, right? So yeah, all these triple summations and probabilities and distributions and so on, in the beginning, they look intimidating, right? But as we discussed last time, and let me quickly refresh your memory, the final equation that we get through step-by-step application of the probability and distribution rules is very, very commonsensical, okay? So let's take a look at the last equation, and very quickly, let's do it via simple example, okay? So let's say—
Good morning, Professor. Today you going to send the attendance code or no?
what was the question?
The attendant?
Attendance, I'll do it in the middle, so that we make sure people are attending and not leaving. So, uh, so but anyway, to me, really, it doesn't make a difference who's attending, who's not, but the university wants it. So we'll have attendance somewhere as I give you a break. Okay, so back to the Bellman equations. Okay, so like I was saying, everything has a very commonsensical explanation to it. So with with Bellman equations, the idea was if we can determine the value of a state, and how do we define a value of a state? Let's say somewhere as we started some video game or self-driving car or whatever, or a robot, whatever, right? So we will come to some state over here. Let's say that state is S. So probabilistically we'll be taking some action, A1, A2, A3, moving to another state, then another set of actions, right? We keep going until either, in case of a self-driving car, either we crash it or we get to the destination. In case of a video game, we win the game or lose the game. So this whole trajectory from start to finish in the RL terminology is called an episode. Okay. So the value of a state, with every state, if we can compute the value is basically if we started from the state and went to the completion, how many rewards we will collect is the definition of the value of the state, right? And because we are interacting in case of a video game or robot or self-driving car, we depend upon how others are reacting. So as we move from one state to another, our movements are probabilistic. Whatever action we are taking has certain probability associated with it. So when we accumulate the rewards, okay, these will also be not deterministic, but probabilistic, right? So we discussed that anytime probability is involved, we want on average, on average, we want to maximize our rewards. So in the math world, whenever probability is involved, the average is referred to as expectation, right? So the formula for expectation, if x is of a random variable, is we will sum x times p of x. P of x is the probability of getting that x, and x is the value, right? So same way over here, what we want to do is we want to maximize the expectation. So if I have to give you, like, what is the high level idea of a value of a state? The value of a state is the expectation of g of t. And what is g of t? G of t is the cumulative rewards, meaning we keep adding them up as we move towards the completion of whatever task we are doing, right? Okay, so that is the, so by looking at the value, if the value is high, that means that state will ultimately lead to a very, very good reward. So if we try to maximize this expectation, right, then whatever policy, meaning policy is the, so another thing, we'll keep clarifying it. Policy is the probability of taking an action. Okay, so the goal in RL is to learn a good policy. So in plain English, so what does that mean? That means take those actions probabilistically such that the expectation of the cumulative rewards is as high as possible. So if we can learn that policy, then our RL system is a very, very good system. If we follow those set of actions probabilistically, we'll end up getting as high rewards as possible, right? Okay, so coming to so the question is, because we want to learn this policy, right? So to learn this policy, as we have talked about last couple of lectures, this is where the beautiful Bellman's equations tell us how should we learn this policy, okay? So we'll translate Bellman's equations into a deep learning network so that it can learn that policy, and we'll tie all the pieces together. So let's try to understand one more time. So let me go back to over here. Understand, step by step, we already talked about, those are simple rules of probability and distributions that will take us to this final equation. But let's see if we can understand this final equation intuitively, okay? So because each step follows a simple rule of math, so that's not the hard part, okay? So let's pick an example. Okay, suppose I have a state S, okay, and let's say there are 3 actions over here, or let me call it S1. Let's go to S2, S3, S4. Okay, so whatever actions we are taking, A1, A2, A3, like I was saying, every action will have a certain probability. Okay, in the beginning, they will be random, meaning they will be equal probability of taking an action. Let's pretend it is not completely random. We have learned a little bit. So the probability of taking the first action is 0.2. Probability of this is 0.3. Probability of this is 0.5. Okay, now, as we take an action, we may get a reward. Okay, so let's say the reward associated with this is 10. Reward associated with this is 20. Reward associated with this is 5. Okay. Sometimes there may be a 0 reward. Sometimes there may be a negative reward. For example, if a car gets into an accident, then there will be a lot of negative reward, right? But to keep this example simple, let's say from here, we further can go to S5 and S6. Let's say probability of this is 0.4, this is 0.6, because there are only 2 actions over here. To keep it simple, I'll just keep it 2 or 3 actions, right? So reward, we can just put 30 over here, 50 over here as an example. So all the rewards, let me put an underscore over here so that we know that's a reward, right? Okay, so let's say the 2 actions we take over here, one takes us over here. Our reward is 50. Other takes us over here, let's say S7. Reward is, let's say, -10. And let's say from S4, one action, and I need the probability, 0.3, 0.7, and let's say 0.2, S8, 0.8 as an example. And let's pick some rewards. Okay, so let's say this is 20. Because I said this is let me make it -20 over here, and let's make it 30 over here. Okay, so let's pretend just a 2-step situation. This S1 is our starting state, S5, S6, S7, S8 are our terminal states, meaning the game ends over there, right? So now the question is, so we want to determine what is V of S1, what is V of S2, V of S3, and V of S4. Okay, so like I said, because probabilities are involved, we will do an average value. So once again, the definition of V of S is expectation of GT, which is the statistical average. And remember, anytime we compute the expectation, keep reminding yourself E of X is sum over all possibilities X times P of X, right? Okay, so let's go to, for example, S2, V of S2. Okay, so what will be V of S2? The probability is 0.4 to go to S5, right? And the reward is 30, correct? So the average, statistical average for the reward, again, I'm applying this type of formula, would be 0.4 times 30 plus 0.5 times 60. So what will that come out to? 30 times 0.4 is 12, and 12 and 30, 42, right? So that will be V of S2. Let's go to V of S3. V of S3 will be 50.3 times 50 plus negative, 0.7 times, so negative 0.7 times 10, right? So here my assumption is this is negative 10, so this will be negative. So 0.3 times 50 is 15. 15 minus 7 will give me 8, okay? Similarly, let's go to V of S4. And in our example, this will be negative 0.2 times 20 plus 0.8 times 30. So which is 24 minus 4 will be 20. So you can see V of S2, S3, S4 have those values, right? Okay, so now let's go see if we can work backwards and find V of S1. So what will be V of S1? V of S1 will be reward is 10, right? And 0.2 is the probability of taking this action, okay? So remember, our definition of G of T was what? This is the cumulative reward up to the end, okay? Now V of S2 already tells us if we started from S2, what will be our reward towards the end, okay? Remember, either we can go this way. Let me use a different color. So either we can go this way from S2, or we can go over here. Both ways we end up towards the end, but V of S2 already gives us the total probabilistic reward. So it's already there. So to get the V of S1, we will use the V of S2 information because it already has the information for statistical average of the total rewards all the way to the end. So as you can see, current reward is 10. So I will do 10 plus V of S2, okay, which will be what? So 10 plus V of S2 was 42, so 52, 52 times 0.2, will that be 10.4? Hopefully my calculation is right. Okay, so similarly, let's see if we can find V of, oh, sorry, this is not the, my mistake. This is not the total answer because I only did it for one path, right? There's another path over here. So then I will need to add to it. Oh, what happened to my computer? You guys can see, right? All right, let's see what happened. Okay, let's get back. Okay, so I was saying that we only did so far this path over here. Let me use a different color. So we only have done this path over here. Right? Okay, sorry, this path. Okay, there's another middle path over here, which I haven't taken into account. So you can see then for the middle path, what will I do? Plus 0.3 times 20 plus V of S3. You guys agree? Then the last path, which is the bottom path over here, will be the reward is 5. And the probability of going through to that path is 0.5. So that will be 0.5 and 5 plus V of S4. Right? Everybody agrees? This will be our value for state 1. Okay, so let's turn this into a math. Okay, so if we turn this into a math equation, what will you find? See, in our terminology, what we were saying is if S is the starting state, the next state that we move to, we often abbreviate it as S prime. So in our example, if S1 is the starting state, S2, S3, S4 can be generally referred to as S prime, right? Okay, so take a look at, you'll see there are 3 components over here. We are adding the 3 components over here. This is one component, this is another component, right? And this is another component. So when we turn this into a math equation, what symbol do we use? Summation. Okay, summation over what? Okay, so see, when we write a summation, we say, for example, if we are going into a loop 10 times, we will say I equal to 1 to 10. So here, what is how many things we are going to? 3, right? And what does that 3 corresponds to? 3 next states. So we will say summation over S prime, right? Okay, and what is this 0.2, 0.3, 0.5? Okay, that is the probability of going to the next state, right? So that is the probability of going to this S prime. And what's given to us? Given to us is what state we are in, which is S, and what action we took, because that will take us to the next state, right? This S prime depends on the action and the state that we were there previously, right? And then what are we doing over here? We are multiplying this with what? This square bracket. Now let's go put these square brackets. What's this 10? Reward, okay, plus, okay, V of, how will I generate, because I'm summing over, see the first time it was V of S2, V of S3, V of S4. In this equation, what will those become? V of what? S prime, very good. Okay, and now because we talked about discounted rewards, we usually use, as we go into the future, we discount them, for example, by a factor of gamma. S prime, V of S prime is the accumulation of rewards from the next state onwards. So those rewards should be multiplied by gamma, right? So so at least this you can see is without even us going all through the derivation of the Bellman equations, we can easily see that is the equation. So let's compare it to what do we have in the handout. So if we go to the handout, okay, take a look at this part over here. So this part over here. Isn't this 100% same as we came up with as a simple example, right? So imagine Bellman spent years and years and we got it in 5 minutes. No, you know, whoever comes up with this formulation very first time is total genius. So we can claim we are as good as Bellman, but uh, uh, but anyway, all I'm saying is it doesn't matter. I can take you through the most complicated math and show you that really behind it, there's a very simple, commonsensical foundation to it, right? So now the only thing you might be wondering is, what about this part over here, okay? And the answer is, if I elaborate on this, I can show you that if I totally generalize it, then this is the probability of taking that action given the state. Is in the general terminology, right, as we are going from S1, there may be many actions and not necessarily every action goes to a separate state. So as we generalize it, there might be another action which takes you to this state, another action takes you to this state. And so as we now sum it over all possible actions, because see, I did it only assuming that states are unique and only one action is associated with the state. Then you will be able to come up with the exact Bellman's equation, right? Okay. So coming back to Bellman's equations now. Okay, so this week I'll give you your first assignment. Okay, your first assignment is just you will redo this handout, and step by step you will be telling me as we went from, for example, this step to this step, what rule of probability did we apply? You'll write it all by hand, okay? Because as we type something, as we write something, okay, our brain works a lot better. And whatever, you know, probability statistical rules we use to go from one step to another. So this will give you a little more practice, a little more, you know, confidence. Yes, you know, I'll share a story with you. My PhD is in electrical engineering. Okay, so like you, when I was a student, okay, I was always curious. Any equation I had, I didn't want to buy it. I want to derive it myself. Okay, as I was graduating, I was interviewing with different companies. And I interviewed with AMD in Pocatello, Idaho, where they had a big plant over there. And their top engineer asked me, so in electrical engineering, we use this MOS transistor. It has a set of equations. So he was asking me, how do you relate the current to the voltage in a MOS transistor? So my answer to him was, I don't memorize things, but I can derive it for you if you would like. He said, okay, show me. So I derived it right in front of him. He gave me the job. Okay. So my advice is, as you're learning, of course, you guys will be applying for jobs. If you can show that kind of confidence, it creates such a good impression. So again, concepts are more important than memorizing things. And so hopefully you guys see nothing complex with Bellman equations, right? Okay, so now next question is, how do we translate it to learning. Okay, we know what is a value of state, but how will the system learn? So let's think about it a little bit. Okay, so our goal, like I said, is to create a deep network. Okay, so like I was saying, let's take a look at the overall goal. Suppose we started with S1. Through trial and error, meaning, if it's a self-driving car, we'll randomly drive it. Sometimes we'll get into the accident. Sometimes it will work fine. If we're playing a video game, a lot of times we'll lose. Once in a while, we'll win, right? So eventually, as we keep adjusting, so all of these values are random in the beginning, but as we succeed, we will keep improving their values, okay? So let's pretend we have learned the values, okay? All the values, no matter which state is, somehow we have learned them, okay? So then how will we use it in real deployed system? The answer is easy. Let's say we start our system. There are three possibilities, A1, A2, A3, okay? So what will we do? We will say, okay, if we are in state S1, if we take A1, suppose the V of S2 is 80, V of S2 is 120, V of S3 is 110, okay? So we will, for all three possible actions, we will see what value will we get, okay? So then what will be our decision out of A1, A2, A3, if this was the scenario? A2, because that will, remember this 120 means that from there, if we went all the way to the end, most likely we'll get a reward of 120. That's the probabilistic average, like I was saying, right? Okay, so the problem is in RL, there could be millions of states. There could be billions of states, okay? We cannot compute the value of each and every state. So the solution would be, all right, let's create a deep network, okay? One possibility is the input to this will be state, okay? And what else will be the input to it? Because the output we want is the value, okay? You can see, because we want to know, right? If we took action A1, this is the number we'll get, okay? So you can see this will be action, which if there were three actions possible, it will take on one of the three values in the set of actions, right? Do you guys agree? Okay, so we'll try, okay. So let's pretend somehow we train this network, okay? We start with S1. So we'll feed S1 over here. And then what will we do? Okay, we'll feed in A1 and it will give us V of S1. We'll store that value. We'll substitute it by A2. We'll feed it to our network. What will we get? V of S2. Okay, if A2 takes to S2, assuming one action always we'll keep things simple in the beginning, then we will generalize it totally. Similarly, we'll feed in A3 and we'll get V of S3. Since we have computed via our deep network three values, now we will see which one is the highest. Whichever is the highest, let's pretend in our example, A2 was the V of S2 was the highest, right? So then what happens? Our action that we will select will be A2. Okay, if it's, let's say A1 in a self-driving car was go left, this was go straight, this was go right. So what action did we do? We did straight, and car moves a little bit ahead, right? So as we discussed in a RL system, that means our environment now has become, it has changed, right? Because the car has moved, so our camera's picture is different. So that is our S prime. That S prime now becomes the next S, right? And now again, we will try those same three actions, compute the three values. So you can see this is how the RL system will be used, okay? Still, we haven't answered the question, okay? Because if we create a deep network, sure, if it is trained, we can use it just like I described it to you guys. But in the beginning, all the weights and biases over here are random. So how is it going to get better, okay? So let me answer that question, okay? And before I answer that question, okay, I'll introduce one more concept. In the example that I gave you, right, how many times we had to go repeat this loop over here to find out what is a good action? How many times we had to feed the data to our deep network to decide which action to take? 3 times, because there were 3 possible actions. What if there were 10 possible actions? 10 times. What if there were 1,000 possible actions? Right? So you can see it works, but it's not a very efficient way to operate. Okay. So this is where in the early days of RL, we came up with value learning. Okay. So if we, by value learning, I mean is we will create our deep network, just like I showed you. Output will be V of S, input will be S, and one of the actions, okay? So the only problem is, like I said, it's not efficient in learning. It's not efficient in terms of deployment because for every action, we have to try and see what's the value we are getting out of our network, right? So then from here, what we did is we said, okay, it works, but that's not a good way to operate. So let's make it Q learning. Okay, so instead of defining the value of a state, let's tie it with Q. So think of Q like a quality of a state. So quality of a state. If that action is taken. Okay, so in our example, think of it this way: rather than relying on a single value for the state, okay, we'll split it into 3 parts. For example, this one could be called Q of S1, A1. This path over here will be Q of S1, A2. And similarly, Q of S1, A3. So what's the difference between Q and V of S? Again, the only difference is value of a state is the probabilistic average of the cumulative rewards, right? Whereas from here, we take that out of the value, we are talking about only one action. If we took that action, what will be our cumulative reward? Okay, so like I said, splitting this calculation into 3 parts. Okay, if we added all of them, sure, we'll get the value of the state. So they are equivalent. But how does it benefit? Okay, first, let me show you in terms of the deployment. In terms of the deployment, if we are using Q of S of A, what will our network look like? Our network will simply take state as the input, okay, and the output will be Q of SA1, Q of SA2, and Q of SA3. Okay, let's pretend in our first example, there were only 3 actions. If 3 meaning go straight, go left, go right, okay? So if there were only 3 actions, then how will we, our camera in a self-driving car, as you can see, is telling us what's the road condition, where are the other drivers, right? So we feed that to our network and it will produce 3 outputs, okay? Which one will we take now? The highest one, because that's, remember, the definition of a V or a Q is the same. If we followed that path, then the cumulative reward, the probability of getting the cumulative reward will be the highest possible, right? So let's say this gave us a value, for example, 90, this gave us a value 30, this gave us a value 110. So which one will you pick? 110, right? So which action will we take then? A3, okay? If there are 3 outputs, we don't even have to, because all we care is, in case of a self-driving car, which action should we take? So we don't even have to take a look at the actual values. Because all we care is what is the maximum of these, and we should take that action. So what if you're creating a deep network, what do you do at the end so that it can easily tell you the maximum? Softmax, okay? So just put a softmax at the end. It will have, if there are 3 actions, there will be 3 outputs. Sum of those, remember, sum of all of these actions will be 1. Whichever is the highest, the index of the highest is the action you will take, okay? So you can see from a deployment point of view, compared to value learning, if we did Q learning, meaning somehow we train this network, we call it a Q network now, instead of a V network, it's a Q network because the outputs it's producing is Q, right? So then you can see, we don't have to loop through all states to find out what is the highest value of the state. So that's why in practice, we don't use value learning, even though theoretically you can use it, we always use Q learning, okay? So let's tie the 2 pieces together. If I go to our handout. Okay, so if you go to the of our RL course handout. So the Bellman equation derivation is in lecture 2 handout. So if I take you to lecture 3, which is deep Q learning, and I'll just show you a few simple concepts first. Okay. Okay, so remember, as we talked about, this is the general diagram of RL. So hopefully by now you're getting very fluent with it. What is the agent in our implementation? Agent is our deep network. Which in the beginning is untrained, but gradually it will learn and do a better job, right? What's the input to the agent? Input is state. Okay, even though in this diagram there's a reward also, we don't feed the reward to the agent, as you will see, just the state. What's the output? It will be in Q learning, it will be Q of S A1, Q of S, many of these. Right? Okay, then whichever produces the highest value, that is the action we will take, right? Everybody agrees? And that will give us a new environment, we'll get some reward, okay? That reward will be used to train the network. So even though in this diagram that reward is going into the agent, it's really going in the formulation of the loss function so that we can train the network, okay? So anyway, then we get this S prime is the S, T plus 1 is, we will refer to it S prime, that S prime changes to S, and then we repeat the cycle, okay? So once again, to refresh your memory, value of a state is the expectation of cumulative rewards, like RT plus 1 is the reward in the next state, RT plus 2 is the reward in the next to next state. And what is it multiplied by? The discount factor gamma, and then gamma square, and so on, okay? Given ST equal to S, meaning given starting state, okay? And expectation means probabilistically will multiply these rewards, as I showed you with the 3-branch example and the 2-branch example, right? Okay, so in our terminology, like I said, S will be the starting state. We'll take some action, we'll get some reward. And where will we move to? S prime. Then similarly, we'll take some action, keep moving until we get to the end, right? Okay, so as I mentioned, instead of using value learning, we'll create a network so that it does Q learning. The output of the network is a Q, which is given a state and one of the actions, it will tell us what is the, if we follow that action all the way to the end, what will be the expected cumulative reward, right? Okay, so anyway, according to, let's take a look over here. This was our definition of the total cumulative reward. G of T, if you remember, was the total. And one of the, okay, let me mention this, and as I show you the math, I'll emphasize it again. Okay, so one of the ideas of the Bellman, remember as we went through that simple example, what did we say? If the value of a state, as an example, is over all possible next state, what is the probability of taking the next state given current state and an action, right? And then we multiplied by R plus gamma, and over here, what was it? V of S prime, right? Okay. So as you can see, the whole philosophy or the thought process in Bellman was, because what he was doing is he was trying to tie it to how can we make it learn? How can we make a system learn given a state, okay? So because a lot of games, let's say you're playing a chess game, right? It may take 2 hours to go and until you win or until you lose, or in some games may take days or many hours to get us reward. A lot of times you do something, nothing happens, right? So what he wanted to do is, let me give you an analogy. Let's say you are in some kind of a terrain, okay? And you are somewhere over here. Right? And there are many paths to get to the bottom of the hill, okay? So like I'm saying, which one is the best way to get down from a mountain? Because sometimes you go up, then you go down, then you go up, and let's pretend it's totally dark, you cannot see, right? So rather than you exploring many of these paths over here, like I said, each time it may take you days to get to the bottom and say, no, or sometimes you may fall off the cliff or something, right? Okay, so Bellman's thought process was, rather than going all the way to the end and then figuring out, what should be our criteria for moving next? Okay, can we just do it incrementally? Just move a little bit, then move a little bit, then move a little bit, keep adjusting our what we have discovered so far. And maybe gradually that will lead to a very, very good policy, meaning very good route that will give us the best reward. Okay. So what he was trying to do is everything, regardless is value learning, Q learning, everything he wanted to describe it mathematically in a recursive form. A recursive is where if you have, let me give you a simple example, okay? Let's say you have 5 factorial. What's the answer? 5 times 4 times 3 times 2 times 1, right? So that is a brute force approach, but we can recursively, how can I write 5 factorial? Can I say it 5 times 4 factorial, right? So the factorial is defined in terms of a smaller factorial, right? Or I can say n factorial is n times. And so this is what we call a recursive definition, right? Take a look at this formulation that we came up with. How is V of S defined? Is it defined in terms of how do we start and go all the way to the end? Or is it defined in terms of simply the value of the next state? You can see over here, there's V of S prime, okay? So all we are doing is we are saying, if we somehow we knew the next state's value, how can we find our value without even worrying about how did we get to the very end, right? So same thing he will do in Q learning. He will define a recursive definition of Q. This way, we will translate that to our deep networks learning, and you'll see everything will work out very nicely, okay? So going back to over here, okay, so let's, I mean, intuitively we saw, right? What's the relationship between, okay, intuitively, suppose this is S1, S2, S3, S4, right? Okay, suppose this is V of S2. Somehow we knew it, V of S3, V of S4. Okay, using Bellman's equation, we were able to relate V of S1 with V of whatever the next state of S1 is, which could be S2, S3, right? Or in general, V of S with respect to V of S prime. Okay, if there are 3 actions possible, A1, A2, A3, like I said, rather than defining a cumulative value for the state, we wanted to split it into 3 parts, right? And reason being, we will like to say this is Q of S1, A1. So if we are in state S1 and we took action A1, what will be our total cumulative reward, right? If we were in state S1 and we took A2 action, how will we end up with the total expected reward, okay? And similarly over here, if we were S1, A3. So my question to you guys is, because we are splitting the value in 3 parts, okay, what will be the relationship between these 3 parts and S1? Say it again. Yeah, exactly. The sum of those should be, right? But remember, it's not the simple sum. So in other words, I cannot say V of S1 equal to Q of S1 A1 plus Q of S1 A2 plus Q of S1 A3. I cannot say that because there's a probability involved, right? So if the probability of taking this action was 0.2, probability of this action was 0.3, and this was 0.5. So now I can do this, right? Okay, how do I translate into a math equation? Won't this be probability of taking an action given a state and multiplied by Q of SA, right? Should it be S prime A or SA? Sorry, V of S. So my question is, should this be S prime or S? And why? It's the current state. It's always S1, S1, S1. That's the current state, right? So without going into the derivation of what's the relationship between Q and V, right? Everybody sees? Sure, we can go through the math, but we can intuitively derive it too, right? Which is what we just did. Let's see if that's the case in the handout. Take a look at the final equation. Right? And what are we summing over? All actions, okay? So piece of cake. Okay, now if I go through the math, I can also show you it is 100% what we got over here as the final answer. So that is the relationship between the value of a state and the quality of a state with an action, okay? So anyway, if we quickly go through it over here, I'm applying simple rules of probabilities and distributions. You will see, okay, by the definition of the value of a state, right, which is the expectation. When we say pi over here, meaning following a certain policy, because the policy will tell us what's the probability of going and taking a particular action. Even though in the beginning, that policy is totally random, it's still a policy, okay? Expectation of the cumulative reward, G of t, remember, is the cumulative reward, which again, we defined it recursively, but if we keep substituting gt plus 1, you will see it will keep becoming, you know, for example, r of t plus 1 plus gamma times r of t plus 2, and yeah, it's hard to write on this one, and so on, plus gamma square, gamma cube, right? Okay, so anyway, that's the definition of the v pi of s, okay? So now if I substitute the formula for expectation, what's the formula for expectation? Remember the formula for expectation, if I have some variable x, is what? Correct? So take a look over here. The only difference is the expectation is conditional, okay? GT given a starting state, okay? So the probability also will be in terms of the expectation, sorry, the conditional. So sum over all GT, it will be P of GT times GT. So just like you know, think of GT like our variable X times probability starting from a state. So the condition comes in the probability condition, meaning if somebody says X given something does not make sense. If you say probability of X given something, that makes sense. So the probability is always associated with if there's a starting state with the condition of the starting state, okay? So up to this part is simply expanding the definition of expectation by changing it to a summation, right? So what did we do in the next part? Okay, in the next part, okay, what we did is, if you take a look over here, we made it a joint over here. Probability of GT comma A given S, right? See, if you remember some time ago, we had talked about marginalization, okay? And let me refresh your memory. If you're given a joint PDF, P of XY, right? And if you sum over all values of Y, what will you get? The Y will disappear and you will get P of X, right? So similarly, if I say P of X, Y given Z, let's say I sum over all values of Y, what will I get? P of X given Z. So this is what we call marginalization, where from the joined PDF, we can extract the individual PDF. So I basically applied the rule of marginalization over here. So if you'll see there's a joint over here, I added A over here, right? Okay, if I sum over all A's, what will happen? So if I sum, won't I get P of GT given S? A will disappear, as you can see. So you can see from here to here is simply the rule of, so from here, I can go over here. So if I marginalize A, I'll get back to my original. So that's what we did over here, right? And now let's go to the next step. What are we doing over here in the next step? Okay, so now what we are doing is we are extracting this A given S out of over here. Okay, because previously GT and A jointly, it was given S. So if I say only A given S, then I further have to go and add this P of GT. So from here, let's see, P of, so I took this AS over here. So this P of AS got over here. So this part, let me just make it, right? So you can see GT is remaining, right? So then GT has to be dependent on S and A. If you go back to one of the handouts where I showed you, if you have a conditional probability like this and you take out one of the variables, then the remaining variable, which in this case is GT, has to be made conditional on both A and S. So again, this is one of the rules of the probability. Now, if you focus on this part, okay, there is some variable over here and there is some probability over here and we are summing. So that is the expectation. So this is the expectation of GT given S comma A, right? And which is the definition of the equality, okay? So in other words, we come up with the relationship which we did it intuitively, okay? Which one is easier, going through all these math steps or just doing it by an example and coming up with the same answer, okay? Of course, doing by an example, coming up with the same answer is a lot easier, but you know, as you get better, you guys are graduate students. If you, for example, try to write a research paper, you cannot say, oh, look, here's an example, and therefore this is the, you have to do it by applying all the rules, and that's what Bellman did. Okay, so to summarize, okay, all I'm saying is all Bellman's equations are very commonsensical. We can show them through a simple example that they are the final answer we can also get. Of course, the rules of probability and distributions as we apply, as I showed you in this case and the previous case, we come up with the same equations, right? Okay, so one time, please go through so that you feel comfortable. It's like having a clarity in your own mind. Okay, this is how it's working. What's, you know, why are we using Q learning? Why not value learning? Okay. All right. So now let's come to the next part. The next part is, okay, so we understand now, hopefully, Bellman's equations inside out. Okay, and the whole idea was if you're given a state, Okay, we can either determine V of S, or we can determine Q of S A1, Q of S A2, and Q of S A3. As we discuss, the probabilistic sum of these is the same as V of S. Okay, so nothing magical about it. From creating a network point of view and deployment point of view, Q learning is a lot more efficient as compared to value learning, even though they are one and the same thing. So that's why nobody uses value learning in applications of RL, only Q learning. Okay, now coming to the more important question. Okay, this network, which will take a input and will output Q of S A1, Q of S A2, and so on. Okay, if we are creating this network, how is it going to learn? Okay, so Bellman also came up with another beautiful setup over here, which is called temporal difference learning. Okay, and let me show you the equations, and then I will give you the motivation behind it. It's pretty commonsensical again. Okay, okay, let me skip this part. Okay. Okay, so the general idea in temporal difference learning is very, very similar to, remember when we create deep networks and we modify the weights. If you remember, okay, let me sidetrack a little bit first. So suppose we have a deep network. Some parameters theta over here, which are the weights and biases. Okay, so how do we make it learn, right? We define some kind of loss function where we have some target values, meaning the expected value. Okay, and okay, from this loss, so we give it some input. The network produces some output. We compare it with the target. Whatever the loss is, whether that's cross entropy or mean square or whatever, then what we do is we compute partial L over partial theta. And then we apply the gradient descent algorithm, which basically says update this theta equal to the old value of theta minus some learning rate times partial L over partial theta. So we keep iteratively doing this, and once this theta is stabilized, then that's our trained network, right? Very similarly in temporal difference learning. Okay, the idea is the new Q value, all the Q values. So again, going to my Q network example. Okay, this example. Okay, all the weights and biases are random. So all these Q values have some initial values. Okay, we don't, in the beginning, right? They could be any number. Okay, so the new Q value that we will update in temporal difference learning will be the old Q value plus step size. Step size is like a learning rate, could be 0.01 or something like this, right? Target value minus the old value, okay? So you can see, just like in a normal deep learning, this part was what? This was partial L over partial theta, okay? But we cannot have a loss over here in the traditional sense because in RL, there is no training data. It learns through trial and error, right? So if we can come up with somehow a slightly better Q value, subtract the current value, okay, use that information to increase the weights, then it will learn. So the intuitive analogy is something like this. Okay, let's say you're learning to play tennis. Okay, you're not a good player yet. You hit a shot and it, let's say randomly, it turned out to be pretty good and you won the point. Okay, so you say, oh, my current style was, like a hacker style, not very good, but somehow I changed it and it worked. Okay, so if I use that where I got tiny bit better feedback or whatever, and now let me adjust the style because that gave me, even though a very tiny reward, and now let me adjust my style. So gradually you keep doing it over and over and over again, you'll keep getting better. So intuitively you can see it does make sense. It's like let me give an example. Music, Scott will get angry at me. You start playing a tune, right? And somehow it sounds better. So then you start adjusting it, you say, oh yeah, what if I refine it a little bit better, right? So that is the idea. So this is what you just experimented. You got a tiny bit better. You subtract, meaning you want to, based on the old way you are now making. So this is the difference is what the improvement is. Okay, and you don't want to drastically change it. So step size will, just like a learning rate, will make sure you are gradually improving it. So you are learning it in a stable manner. Otherwise, you'll get better, you'll get worse, you'll get better. So you can see intuitively, it does make a lot of sense. Okay. So okay, and so I'll put more detail over here in a second. But anyway, so how do we determine the target Q value? So we'll go over here. So if I give you the actual formula in the Q learning algorithm, the actual formula is Q of ST new. It will be the old value. Like I said, alpha is the like a learning rate or a step size, so 0.01, something small, right? RT is what? Reward if taking that action, because every action may give you a reward, right? Plus gamma times, what's gamma over here? Discount factor. Okay, and then the maximum of maximum over all actions, the Q of ST plus 1A, okay? And this is the old value. Okay, so let me clarify this. Okay, so think of it this way. Let's say you are here in this picture over here, right? Okay, so this is the old value is Q of ST of A old. Okay, as we take an action, we'll get a reward. So that's R of T over here that you see over here, right? Okay, so now we will go to ST plus 1, a next state. Okay, but from next state, there are many actions possible. So let's say A1, A2, AN, right? Okay, for all of those actions, what we will do is now we will determine what is the maximum Q value, okay, as we leave the state. So there are, okay, let's say over here you have a value of 20, meaning Q of ST plus 1, comma A. is 20. If you took action A1 on ST plus 1, you get a reward of cumulative reward all the way to the end. Let's say this is 30. Let's say this is 50. Okay, so again, these are Q of ST plus 1, comma, A, as we take the action on this ST plus 1. Okay, so that maximum, okay, we will use as the target. Okay, so now let's pause for a second. Do we want the target Q value to be good or bad, or we don't care? For it to learn to take better and better actions as it goes along. We want it to be good, right? So, so does the taking the maximum, doesn't that give us the better action out of the three? So you can see that is why the path it's telling us to take is the one where the Q probably will be better. So this maximum is very important in terms of unsupervised learning, because we want the target to be a little bit better. Okay, if we did not pick this to be maximum and we said pick any, it will never learn anything. Okay, so that is the idea of this incremental learning. Pick the target by taking a look at if there were three possibilities, which one gives me better option, better total reward at the end, right? So still, okay, so let's pick an example to have a better intuitive understanding of it. Okay, so each one of these actions has in the beginning, right? Because remember, we will be creating a network over here with some state as the input and QS of A1 and QS of A2 and so on. Okay, so in the beginning, this is randomly initialized, all Q values. So even though the Q values exist everywhere, they are pretty bad, right? Because they are all random. So let's say we started over here. Okay, so as I mentioned, we will pick one action. Suppose this is what we want to adjust. Okay, so what will we do? Let me use a different color. Okay, because we picked this action, that means we are coming to this blue one. Okay, so the question is, to adjust this Q, we need a target Q value, a better Q value. So how will we get that better Q value? From here, there are three possibilities. Okay, even though they were random, let's say this was 15, this was 18 in the beginning, this was 21, right? So what will the target be used to adjust this? It will be 21. But you may argue, hey, in the beginning that's random, so it's how is it getting any better? Because remember, we'll keep going. We will complete a full episode. In the end, sometimes we will win. Okay, so as we repeat this process of many times and keep adjusting, this target Q will start to get better and better, because eventually we'll win. Those values at the end will end up adjusting the Q over here, which will go backwards, adjust the Q over here, and so on. So this is how it will eventually learn. the completion of the episode and once in a while getting lucky to win is critical to learning. Okay. So anyway, let me, so hopefully these, like I said, the key parts in the learning are this general idea. Because RL is unsupervised learning, we say, okay, go to the next state and then find out which three of them might be, which is the best of those. And then try to orient yourself so that there's a high probability of going towards that path. Same way over here, if this is where you came, again, you will take three paths. In whichever way is the highest, now you will adjust your probabilities for the cues. So there's a higher probability of going to that path. Ultimately, like I said, this will give us total cumulative reward, which is as high as possible, right? Okay, so let me do this. Let me give you guys a short break. And after the break, we will put this into a neural network form and see if we can make it learn. Hey, anybody who just joined after the break? Today's attendance is 9459. So if you guys can please go to Canvas, quickly attendance marked, enter the code 9459 for today's attendance. Hey, all right, so let's get back to our, so
I have a question for the report. So, example of LLM. So first we're gonna do the auto regression, and then we go with the RLHF. So when we are doing this step, it's like fine tuning based on prompt and then
Yep.
ideal response.
mhm.
So the reward is the ideal response. But the action is gonna be the next token.
I think LLMs are trained in two steps. Okay, one is where you focus on the prediction of the next token, where you use the cross entropy loss. Once you fine tune it for RLHF, you don't take a look at precisely the next token. You adjust the policy on the entire generated sequence. How do you do that? At the end of the course, we'll be doing an assignment and that will become clear. Okay.
Professor, just I have a little bit clarifications.
Okay, so coming back to our reinforcement learning, like I was saying, very quickly to emphasize again and summarize one more time. Okay, one
can I
option
ask the
is to
question?
learn the value of each state. So one is this option, learn the value of a state. Another option is learn the quality of a state for each particular action. And as we discussed, implementing it this way is a preferred approach because it's more efficient at the deployment level, right? So RL started out with Q learning becoming very popular. And to get a better handle on Q learning, now our next goal was, like we discussed before the break, how do we make this network learn? Because the network will take state as an input. It will have many of these QSA as outputs. For each action, there will be a separate output in the beginning. Then we'll refine it, go into different categories and so on that you will gradually see. Okay, so the part that is still a little bit ambiguous right now is how is it going to learn? Like, what is our loss function going to look like? And how are we going to translate into updating these weights and parameters, right? Okay, so to answer that question partially, and like I said, gradually we'll put full detail in it. We said that the general idea was the new Q value will be updated by the old Q value. Then we'll have a step. There will be some target Q minus the old Q. Okay. So the question was, in supervised learning, there's a precise target given to us. In RL, there is no target. So how do we find this target towards which we want to improve our network? And the answer was just go 2 steps ahead. And then for this, you go 1 step ahead. And then from that step, let's say there are many actions possible. Whichever is leading to the highest Q value, take the maximum of that and use that as the target over here. So you can see max of A over all actions from the next state. And then you subtract the current state, multiply by a step, and that's how we will update the Q value, right? And intuitively, that does make sense. There are 3 possibilities. One of them is a little bit better. Why not adjust ourselves? Like I gave you the example of playing tennis or playing any sport. You try, and if one of the actions is giving you a little bit better reward, you adjust your policy, meaning your style, towards that. So that's the intuitive idea, right? So to get better at it, step at a time, I'll start out with a very, very simple example and show you how we will make our system learn. So this is a simple, famous example. It's called a room example, where the idea is you're given a set of doors and set of rooms. And depending upon where you start, you need to figure out which door to go to so that you can get out of the house, okay? For example, if you take a look over here, if there's room 1, room 0, room 4, room 3, right? When we get outside, in this case, we're calling that state 5. So for example, let's say we start with 2, okay? What will happen? One possibility is you can go to 3, right? Then you can go to 4. Okay, and maybe then you can get out over here. That's one possibility. Or you can go to 3, then you can go to 1, and then you can get out over here. So the idea is to get outside the house. So, and of course, we want to accomplish this in as less number of steps as possible. So what's our learning, Q learning over here, so that once the system is learned, we can easily go through, right? Okay, so when let me go over here. So in Q learning, right, we are learning a joint distribution of states and all actions, okay? So these are all the states, and these are all the actions. Okay, when this joint set is small, then what we can do is, rather than creating a network, we can simply create a table for small cases. Okay. Of course, if the combination of these is huge, then we cannot have billions of entries in a table. That's when we will switch to a deep network, and you'll see it will be able to estimate the values and learn and proceed. Okay. So anyway, for our first example, if you take a look at this part over here, it's very easy to follow. For example, this is the state sequence, and for every action, there's a reward. So this 100 is a reward. For example, let's say you are in room 3, okay, which is 3 is where? Over here, right? From 3, what's the possibility? You can go to 1. or you can go to 4 and get out, right? So from 3, you can go to 1, and you can get out, which is 5 over here, and you will get a reward of 100. Okay. From 3, you can also go to 4. So from 3, like I said, you can also go to 4 and then get out. Okay, so as you go from 3 to 4, the reward is 0 because you haven't gotten out yet. So in a lot of cases, you get the reward as you get completely out. Okay, so then as you go from 4 to 5, you will get a reward of 100. So this is our state sequence as we move between different rooms. Because these are just 4 or 5 rooms, and you have 5 actions over here, or 6 actions if you count 0, 0, 1, 2, 3, 4, 5. Okay, 6 actions so we can easily fill that into the Q table into a 6 by 6 matrix as an example. Okay, so to set up this problem as a Q learning, okay, the reward also, as well as the Q, both of them will set up as a 6 by 6 matrix. Okay, so let's see if this reward matrix makes sense. Okay, let's pick, for example, this is the starting room, 2. Okay, so suppose from 2, which is where it's 2 over here. Can I go from 2 to 4 directly? No. So if you take a look at 2 to 4, what do you see? So -1 means that's an invalid state. So we can come up with some terminology for ourselves. So remember, this is a reward, means it's a negative reward or invalid state in this example. So from 2, can we go to 0? No, so you'll see there's -1 here as well, right? From 2, where can we go? Only 3. Okay, but we haven't gotten out. So what's the reward? 0, right? Same way, let's take a look at if we started with 1. So if we started with 1, can we go to 3? So 1 to 3, what will be the reward? 0 because we haven't gotten out yet. How about 1 to 5? Can we go 1 to 5? Yes, so the reward is 100. So given this environment, it's a static environment, unlike a self-driving car, which will be changing and probabilistic. So this is easy. We can create this reward table by looking at all possibilities. So this is given to us. Okay. Now let's go, how will we set up the Q learning so that given any state, we'll follow our learned Q to get out of as quickly as possible, okay? So now let's take a look at the Q learning. Okay, remember the equation for updating the Q I mentioned previously was, let me see if I can, okay. Okay, the old equation, if you remember, it was something like this: Q new equal to Q old plus, there was some kind of a step size over here, or let me just put alpha over here, right? There was some target Q over here minus the Q old, right? And this target Q was determined from maximum over Q values over the next state, or maximum over all actions on the next state, right? Okay. There was a okay, let me just go back for 1 second just to clarify. Oh, sorry, it was right here. Okay, so in the calculation of the target Q, in the calculation of this target Q over here, you will see this is where the current, the immediate reward plus maximum of the Q values from the next state was, so this was our, this reward was put inside this target Q value, right? So, so now we could use that, but we are going to make it a little bit simpler over here in this case. So in this particular case, we'll just say, let's update the Q. So this is a simplified version of the full Q learning equation. So reward plus gamma times the maximum. Okay. Even though it's not the same equation that I showed you, this also works, like I said, because this is such a simple problem. But when we set up the deep network, we'll go back to the equation that I showed you earlier, right? Okay, so let's see how the, so this is our Q table. So Q table also will be a 6x6 table, and we will initialize it with all zeros. So Q table has all zeros, right? Then what we will do is we will randomly start at one. So random start. Let me see if I can. Okay, so we will do a random start, meaning whatever room we are starting will be randomly picked. And we will complete the episode, meaning we will keep trying until we get out, okay, in this example. Okay, because we are going all the way, and we will repeat this many, many times, and each time we will update our Q table according to this formula, okay? Now, as we are moving, starting from a random state, okay, if there's an invalid room, we will try again until we get to a valid room, meaning there's a door to a room. So anyway, let's suppose we start at room 1, okay? So room 1, think of it this way, we are starting over here, okay? Can I go to 0? No, okay. So like I said, as we start, as I, you know, in your next assignment, you'll be implementing this. And what you will see is what we are doing is we'll randomly pick a start, like I showed you over here. Suppose we pick 1, okay? Then you will go into a loop. You will randomly pick next room. So randomly pick next room. Okay, if that room is -1, you will keep repeating it until that's a valid room. Okay, because the idea is to move. What I'm trying to say is, okay, so let's say you started from 2, right? You picked randomly room 4, but you cannot go to 4. So you're stuck at 2, okay? The idea is from S, we want to move to S prime, then S double prime, and so on. So as you can see, if we don't go to 3, we will not change the state. State stays the same. So in our code, pretty soon you will see the code is written such that you keep saying, okay, let's go to this, let's try this. If it is not a valid room, try again, until you find valid. And that becomes your next state. Okay, so if we go, where did it go? Yeah, over here. Okay, so anyway, as we were trying randomly from starting from room 1, right? So let me go. Okay, so we tried, let's say, first time 2 randomly. It says -1, so we cannot change the state. We try again. Let's say it came up with 1. We cannot go to 1 either, right? Let's say somehow randomly we picked 5 to be the next room. Okay, so that's what I'm indicating over here. Let's say the code picked 5 to be randomly the next room. Can we move to 5? Yes, it's a valid possibility. So then what was the old value of Q? Old value over here was 0, right? So what is the Q of the next state? All actions. So let's try to figure this out. What's our next state in this case? 5. So if I go to 5, what is the maximum of all actions? 100. So you can see the current Q. So Q of 1 of, so what I will do is I will say Q of 1, 5 will be updated as how? R of state action, okay? So R of 1, 5, right? Plus gamma, let's pretend is 0.8 in our example. Okay, 0.8 times maximum Q of all next states, right? So what is the Q value of all the next states? Okay, so not the reward, but the Q. What were Q initialized to? Zeros, right? So these are all zeros. But what is reward of 1, 5? 100. So that's why R of 1, 5 will get changed to 100. Okay. Let's try again. So now because we starting from 1, right? We started at 1 and we randomly ended up we ended up selecting 5. So what will be the next state then? 5. Okay, so now 5 becomes our current state. So now we will do starting from 5. We will again try. So let's go to 5. And we'll again randomly try what room can we go to. Can we go to, for example, what if we pick 2? Can we go to 2 from 5? No. Can we go to 3 from? No, right? So let's pretend from 5, we ended up picking, can we go to 1? Yes, okay. So now let's see, because from 5, we can move to 1. How will Q of 5, 1 will be updated? Q of 5, 1 will be, according to our formula, R of 5, 1 plus gamma times, okay, maximum of next state. What's the next state now? 1. So in our Q table, not in the reward table, in the Q table, we'll go to 1. And we will take a look at what is the maximum of all actions over here. It is 100. So that will come up 100. And what is gamma over here? In our assumption, it's 0.8. So what will happen here then? R of 5, 1 was 0. So this is 0. Plus gamma is 0.8. 0.8 times 100 will be 80. So this is why this is 80. Okay. So the confusing thing over here sometimes is, are we taking a look at the entry in the R table or are we taking a look in the Q table? Okay, so keep reminding yourself, and don't confuse the two. When we go to this max of this, okay, this is based on Q table, not the R table. Okay, this one data will come from which table? R table. Okay, let me give you one more example and see if that makes sense. Okay, let's go to this example over here. Okay, so as you can see, we keep going through, pick a random room, keep trying next room, next room. If it's a valid room, we keep updating the Q table. So let's pretend at some point in time, this is the status of the Q table. Okay, if this is the status of the Q table, and let's pretend we started from 1. Okay, and now we picked 5 as the next one. So let's try to fill this table. So how will Q of 1, 5 will be? This will be R of plus 0.8 times. Okay, Q of 5 onwards. You guys agree? Okay, because the next state in this case is 5. Okay, so remember that has to come from the Q table. So if we go to Q of 5, which is this last row over here, what is the max over here? So you will pick 80. Okay, what is R of 1 comma 5? 1 comma 5 is 100, right? So you will see this is 100 plus 0.8 times 80, which is 64. So what will happen to Q1 of 5? It will become 164, right? So like I said, the general philosophy to do the Q learning over here is, like I said, start from a random room. Okay, go into a loop until a valid next room is found. Okay, once you do this, then you will go update Q of start room and valid next room. And once you update, this is where you will do Q of S comma A equal to reward of S plus gamma max of all actions on next state. Okay, so you keep update. So this is our update rule. Okay, and you keep repeating it. So we'll repeat this whole process many, many, many times until Q table is stabilized. Once the Q table is stabilized, so let's go to, sorry. So let me take you back to the handout and okay, so if we wrote the code for it, after I forgot how many iterations, you will see this as the oh yeah, I did say 100. You are right. Okay. So after 100 iterations, this is what the Q table looks like. Okay. Now, this has given us the policy to get out very quickly, doesn't matter what room we start in, by following this queue table. Okay, so let's figure out how. Let's say you start with, what would be a good example? Let's pick room 0. Okay, so once queue table is updated, we follow the queue table to move, right? And so by looking at the queue table, if this is our start is 0, the first row, this is our room. All we do is take a look at the maximum entry in that entire row to figure out where should we go next. What do you see the maximum value over here? 4. So now we are saying move to 4. So now we will go 0, 1, 2, 3, 4. So we come over here. Okay. Again, we'll take a look at all these over here to see where should we move next. So what is the highest value in this row? So now we are saying, okay, move to 5. Okay. And 5 is our finish, so we are done. Okay, so basically we are saying, if you were at 0, go to 4 and get out. That's our 5. Okay, so same way you can pick any other possibility. Let's pick 2 as an example. 0, 1, 2. If we were starting at room 2, how will queue table tell us where to go? Again, what you do is you go to the maximum entry. And what's the maximum entry? 0, 1, 2, 3. So it's saying go to 3. So now let's go to 0, 1, 2, 3, which is this row. From 3, what is the possibility? Yeah, you'll see there are 2 numbers which are equal. Okay, so if that happens, you pick any one of them. Means both are equally, have equal good quality. So if you picked, for example, let's say 1 over here, now you will go to 1. And from 1, which is the highest, 5, which is our goal state or the end state. So we get out. Okay, so this is what you will be doing. So let me do this for today. Let me stop at this point and give you 2 assignments for this week. I'll quickly show you and I'll put it on Canvas as the due. So okay, so assignment 1, again, I'll put it on Canvas. Like I said, this is simply, you will rederive the Bellman equations and tell me, you'll write it by hand, not resubmit and a screenshot of this. You'll submit a screenshot of your handwriting, okay? Like I said, our brain works better as we are typing an equation or writing it, right? And you will give me a brief as I go from one step to another, what rule in the first handout on the background on probability and statistics, which rule was used to go from one step to another, right? Okay, and so that is assignment 1, so that you feel comfortable with both the 2 things that we talked today, which was the derivation, the final equation, Bellman equation, and the relationship also between VS and QS that we saw very intuitively. It's, so it's no longer a scary equation. It's a comfortable equation, right? So that will be your second assignment. Let me see. Yeah, second assignment is the Q room example, but you'll be, programming it in Python. So all the code is given to you. If, I know some of you are very good at Python, so this will be piece of cake. But if you are in the beginning, intermediate stages, again, don't copy and paste the code, because then you're not really picking up the programming concept. Type it, you'll make errors, try to figure out why the errors are. And hopefully you'll be able to, again, it's not a long code, maybe 2 pages worth equivalent. And you will be able to see how the final Q table is. You can easily verify, as we just did, if it's working or not, right? Okay, and gradually, like I said, next time we will make it more involved. And instead of using a lookup table, we'll put a network. The advantage of a network is because if a table has billions of entries, we can't handle it in the memory of our computers. But a network, we don't have to give it each and every combination. It can interpolate from even some things that we were never given to it. It can learn and give us the answer, right? Okay, so let's start programming and let's start learning. So I'll stop at this point.